The big one.
Interior, is that overkill?
No, I just wasn't sure if we should bring it or not, but do you think we can just bring it aside? Yeah,
I mean,
it's sitting there, yeah.
We just load it with whatever we need and then
Okay, yeah, that, we can do that.
I think it will save us a lot of
Yeah, back and forth. Yeah.
time, right?
Yeah, I just don't know if anybody's using it, but maybe they only use it if there's like, maybe on Wednesday when they have their tea time, they might use it.
Let me check with Phil.
Yeah, yeah.
I have the lasers for that. The one, nothing, we don't have any. The lasers used. Yeah. Okay, so not the much. Yeah. Okay, good. And also understand, if you want to choose tracking, or can one, will, you cover one, you cover one, whether one of these, cost zero. While, essentially you always have the strategy staffing or along, and that's how you get,
So things become nicer, more comfortable. Okay, let's discuss maybe, or for lunch or something.
Just getting a little bit more charge.
Okay, what
Because
is
we
this?
were down to 1 bar.
Okay.
So just.
Is it charging you?
Yeah.
Okay. And I think the live, thing is working. It's working earlier. Can actually send it also to Gary because he said it's not going to be. Okay. Look at this 24. Yeah. Yeah. The qualities are chosen because,
Is it live?
yeah, probably 2 seconds. That's okay. That was there. So, oh, is this sorry, because we were using this one. Sorry.
So let's see here. Is this plugged in? Charging.
Yeah, occasionally we wait for the crowds.
Yeah, that's perfect.
So we're not in a huge rush.
I think so if they're going to come, they can just help us. I'm not sure if they'll find it as
Cool.
easy as we
Oh,
do.
let them and, but it was easy getting in, like, did you have to argue the cards or?
Yeah, so we still have to give our driver's license and I think we should, so we sign go through all that.
So we showed the thing, and they said also you have to.
Yeah,
you
yeah.
have to drive the license.
That's right, the driver's license and ID.
So they did take it seriously for some reason. Yeah, otherwise we have a kind of we get over.
Yeah, we're. It's just some,
Yeah, no, but, you can also, where we. So this is for the live stream.
Yeah, just having a look at which, so those two boards are the ones that,
You can also use that.
okay,
You can also use both.
cool.
And we will pan the camera. Oh, God. Yeah, it's additional broken card.
That's right, yeah. Still gonna be there for another year at least. Yeah, it's been great. Yeah, I know most of my family's down in the Cape, so we've seen my parents a lot. We've seen Chantel's parents a bunch. It's been really nice. She's still working in Johannesburg.
Would like to go through?
She sells it once a month. Thanks, how are you? So she gets fine with it. She's actually in Kenya. Really? Yes, I know. So we're finishing up a deal there in Joburg. She flew international on Sunday. I scheduled it to fly around at the same time the next. So, it's been great. Yes, absolutely. Absolutely.
Should be,
Everything looks good.
so where will you be sitting? Will you be in charge of the planning?
Doesn't matter.
Okay.
You know, so
Okay, so can you sit there or?
I think I'll have to see, yes.
Okay. Can bring it a little bit back to
We're a little tight on cable,
you. Okay.
so I could back it up a little, but that would be the mix.
You're right here. Okay. What happened then with the boiling water? Are you using the small one?
Yes.
Oh, it's, even it
It's not
needs,
really,
yeah,
I think I have a plan on how to take care of it.
okay.
Where's the new one?
Oh, I didn't actually see one, but, yeah, yes.
Very good.
Not yet. And these stoppers also for the extensions.
Okay, the company, so,
But you will at least see all this.
Yeah. This table, okay, it's good for the notes.
Oh, no, it's perfect. I can put it down as well. I'm just wondering, it's gonna look better on the, yeah, that way.
But then you can use all the lower iPad dashboard. Using quick course series. Just do one, that's it. You'll see, just walk. And it's kind of even in the middle. Yeah. Because you're not going to use the screen also. So now at least, yeah, and it's actually you can use it for your notes.
That's true, yeah, I can still.
It's just not in the way. I don't think it's. Yeah. That is. Yeah, actually, one of them. Okay, so, you're not in that position. I can go with you. The date is just, everybody get, no, they want me.
Sorry,
No, it's all good, it's all good.
I was wondering what you were waiting for.
It's all good. I mean, we're not tied down. I'm going to be standing for 2 lectures now, so it's just to go and just rest a little.
Get some rest while you can. Yeah.
So that should be checked in codes. Sorry? So that should check in codes.
Yeah, they check out. It's
You also different people, or it's the same thing?
different.
Yeah, it's quite extensive.
And you need and you need ID, some form of identification as well. So.
Because in the past, it used to be the same pin code, but everybody was getting the same pin code for the day, so that, that day. Or, now it's interesting. To have a list of pin codes and names.
They have devices and
Yeah, I think so, because they verify your name, I mean, your ID with the name.
But you still need to make sure you're who you say you are.
Yeah, and then that it matches the pin.
student card or anything like I go to things on any here, but I have to change my passport.
Oh.
I use it.
Yeah.
I don't know.
But even the other times that we would have lists, like we were getting lists for each case, they were actually harassing people like, that sometimes it was arguing with them that, why are you coming here? Even though you were on the list every time.
Oh, wow.
Sure.
So how do you see the power?
Oh.
Decent breakfast.
I just had a power bomb.
Yeah.
I'll have some breakfast tomorrow. That's,
I actually wasn't expecting it. I thought it was just a series. Very good.
yeah.
But I see those who have. Kind of stuff. There's no problem principles, but I'm sorry. They will go. Just get shifted back.
Yeah, sure.
It's difficult for them. But it's not too early.
Is it a biggish group of income?
Before people.
Hey guys.
We had to get to cut for them and get a few of tomorrow. Yeah, tomorrow, Mike.
Disinfect your hands. All right. Good. So, welcome everybody to this 12th Joburg School on string theory. And we're very pleased to have Jaco here. Start. We're much looking forward to it.
Thank you, Kostas, and thank you to the organizers for the invitation. And it's really great to be back in Joburg. Now, I, of course, my host of the birds for a number of years, my first time here. So it's really, really nice to be back. And these schools have always been excellent. So really happy to be here. All right, so what I want to be discussing in these lectures is quantum chaos and complexity. So I envision that the first half, so the first two lectures, will be dedicated to quantum chaos. And then we'll gradually transition to quantum complexity. And describe why it's relevant in studies of quantum chaos, why it's relevant otherwise. So what I will start off with today is just quantum chaos. And I should add that I have in mind that the discussions will be quite pedagogical. I'm going to try to keep the maths to a minimum, but I'm going to try to just sketch some of the details. And if there are more details necessary, then we can just discuss either in the lectures or afterwards. Also, if there's any questions that we can, please interrupt me, and we can have a discussion further from there. So all the element of it. All right. So starting off with quantum chaos, I think the best starting point for this is actually just to discuss chaos. What do we mean by that classically? What is a classical notion of chaos? And we have some good idea now. It's a pretty well developed idea now. Some of the classical chaotic systems that we know is weather. So weather is a chaotic system. This is the setting for the famous butterfly effect. You might have heard. There's a butterfly flapping its wings in Brazil that causes a hurricane in Texas, either on some later stage. The weather is the setting. It's a classical chaotic system. I'm going to describe why that is the case and what that means. But the more physical system, or one that's been theorized, is something like a double pendulum. So in the double pendulum, you take a single pendulum. Of course, a single pendulum is a very simple harmonic motion. But to the end of that pendulum, you attach a second pendulum. And now you trace the path of that second pendulum in space. And that is a chaotic system. It traces out a huge number of paths. And another one that's also classical is the three-body model in gravity. So this is maybe a simulation that you may have seen before. If you have two gravitational bodies, then the motion is again very nice and harmonic. Something like a single planet coming around the sun. But we now include the effects of a planet like Jupiter, and then it starts introducing elements of chaos into this classical system. But to make things a bit more concrete, one of the nicest problems to study, which I'm going to spend a little bit of time on, is the Sinai boulders. So the setting for this is it's quite a simple one. You have in mind some billiard table, some setting on which you have projectiles. Things button, one is typically a rectangle. But you can choose, there's also circular choices. But starting with the rectangular one, you have in mind some projectile, and I'm going to be firing it off in some direction. In other words, with some momentum along the x-axis, some momentum along the y-axis from some position. And then it's going to be, tracing out some path as it's traveling along this momentum. The interaction of the wall is such that if it interacts with the wall, then over here it's going to take the y momentum. I'm sure that it's going to be some axis over here, the x and y axis. When it interacts with this wall, or it links with this wall, then py goes to minus 2. And the same for this wall on this side, and here px goes to minus px. It's a sort of hard wall interaction. Rise, maintains momentum, it just flips side when it hits the wall. Now, this system over here is that I've sketched is an integral system. It can be exactly solved, and it has some features that are going to be relevant that we want to contrast with our systems. So, a nice way that it can be solved is to, well, you have this grid over here, you just duplicate it a bunch of times. You isolate the whole XY plane with these. So I'm just going to draw a couple of copies of it. Not too many, I just want to illustrate the idea. So let's say that we take that particle as it's sketched at the end, so it's not at this point. And of course, it's going to go into this wall, and in the physical picture we have in mind, it's going to flip its y momentum and go back in another direction. But in this grid, what you then mention is, I'm going to distinguish this as the top part of the grid. And in this grid, I'm just going to sketch this as a straight line going on. And the way that you should visualize the motion in this second block over here is that it is flipped relative to this top block. So in other words, this is just sort of a means to solve the problem. But what's nice about this is that in this sort of space, the solution is a straight line. And I can imagine each one of these boxes, to get the physical position of the particle, I just need to do a set of flips along the top part or the sides of this box. And of course, if it hits the side over here, I need to have a second color that's just indicating to me the orientation of this. So it's only going to be a combination of X flips or Y flips to get me the physical position of that particle that's momentum inside the box. What's nice about this picture is it makes it very obvious that if I take two particles and I shoot them off the same momentum and roughly the same position, then they're always going to be tracing the same path, or almost the same path. It's going to be really close to one another in this picture. Right, so of course, you get the physical motion in that box. It's going to involve all sorts of rotations. I can incorporate that with just simple flips in this picture. And here, it's pretty obvious that if I take two particles and I shoot them off, they're going to remain close to one another. And this is a signature of integral planes. Essentially, I take two particles with slightly different initial conditions. That's going to play a big part. If they're slightly closer at the beginning time, they're going to be slightly closer at the beginning time, they're going to be slightly close to one another. Now that's the one feature I want to highlight. That there's not going to be it's not really sensitive to the initial choice of conditions. It's the motion initial choice of conditions. The motion is very simple. Two particles close to one another, overnight close to one another. That's the one feature. The second feature that I want to point out is that if you think about the motion of this particle in this box, the number of momenta, or the amount of momenta that this particle is going to maintain about its motion is going to be extremely limited. It's going to be your initial momentum, x momentum, and y momentum. You're going to have minus px py. At some stage, you're going to have px minus py and minus px minus py. So these are the components of the momentum as it's traveling around the box. At some stage, it's going to have these, but it's only four possible ones. Only these four. So if you think about the entirety of phase space that particle is moving through, it's really interesting. So it's foreseeable that it might cross a large number of space points. But in terms of the number of momenta, it's going to be a very limited number of only these four possible solutions. So it's only going to be tracing like paths in four lanes in this really big phase space. So the number of paths that it's tracing out in the system is extremely limited. That's the second feature. This is typical of integral dynamics. You can think of the pendulum motion, for example. The number of position and momentum components that's stressing out in phase space is extremely limited. Right. This tessellation idea works for these blocks, but it works nicely for a number of other choices for these audio tables. So one other possible choice you could play, for example, is an hexagon. And with the hexagon, you can tessellate the two-dimensional plane small. And with a similar sort of idea, you can construct this. This is again an integral system. It's going to have the same sort of features. Here, you'll just have a collection of, I think it will be, I'm not going to count the number of momenta, but also a small amount, probably 6, if I was to guess, but I think we can on that. But the point is that, again, you're going to have these same two features that you shoot the particle with a slightly different initial condition, you're going to have close, and the number of points that it's traversing in phase space is extremely limited. Those are the two key features. What you can do with these Gaussians, however, is make a simple change, like you did with the double pendulum or the three particle, a change that seems quite innocent, but changes the dynamics of the system completely. What you can do is introduce a barrier, for example, in the system. So instead of just a regular triangle, what you consider is a rectangle. What you could consider is a regular rectangle with some circular obstruction. Seemingly very innocent change that we make in the system, but it has a dramatic effect on the motion of this particle in this plane. So let's take the first observation that we made, for example. I take two particles, shoot them off with slightly different initial conditions. But what's going to happen to their motion? So I'm going to make a choice that illustrates it. Most dramatically, but at some stage, this situation is going to occur as it is traveling. So let's take a particle that's here, fire off this momentum, and the second one fire off with the same momentum, a slightly different position. Now what's going to happen is that this top particle is going to hit the circle over there, and this bottom one is going to hit the circle. And what you can already see is once they interact with this unseated barrier, this one is going to fire off approximately maybe in a direction like that, I would imagine. And this bottom one is going to go towards the bottom half with a very different momentum as well. So I've taken two particles with almost the same initial condition in phase space. And due to this barrier, after only a short time, they are already at dramatically different parts, different momentum, different positions of the voltage. So this first condition is clearly broken down, and we observe in this integral system.
So, in the second feature, so it can take any value of moment, right?
That's right.
But you're saying that something runs of moment in the second, right?
So you just repeat that.
Yeah, it can take any value of moment based on their location.
Absolutely, and that's an important feature. When we had in the first system, there was a limited number of momentum that it could take. So it was only 4 different values for the space of the rectangle. Once we introduce this circular obstruction, of course, depending on where it hits the circular obstruction, the momentum can be in any direction. And that's the second feature that is also broken down. So this first feature is that it's it's sensitive to the choice of initial conditions. And secondly, if you think about the number of points in phase space that it's going to populate, it's going to be almost all of them. Yeah. All possible positions in the Boolean table, all possible choices of momentum. And the system seems quite innocent. You would imagine that something like this, where the interaction is very well described, can be exactly solvable. It's not. You have to use numerics in order to solve the system. You cannot solve it analytically. like you would for the integral system.
So it is broken.
Absolutely. In fact, the system over here is chaotic.
Did you specify the interaction of the particles with the?
Oh, that's a good point. Yeah, the action will be similar to what you have here, where you have just a reflection on the interaction with the circular barrier, take the tangent of that circle, and connect to that point of there, and it's just going to reflect the momentum that, just a hard reflection on this tangent. So that's what it's described. And here you can see that, well, as you move around the circle, this tangent line is going to change, and the outgoing momentum is going to be very sensitive to where exactly you connect to this circular barrier. Right? So it is going to be very sensitive to where exactly you connect to this circular barrier. Right? So these are two features that, as I mentioned, are broken. And these are two features that are typical of chaotic systems. There's a sensitivity to the initial conditions, in fact, an exponential sensitivity to the initial conditions, and there is this population of the entire phase. This is called overviscity. So at some point, it's going to be populating every single point. So you've got a four-dimensional phase space, two components of position, two of momentum. All of them are all accessible points will be populated. Obviously, a particle can never find itself inside the barrier, but besides those restrictions, all of those points will be populated.
Which I can customize the plane with quadrilaterals as well. So, for example, a rhombus. Is billiard motion on a rhombus is it chaotic or is it integrable?
I think it's integrable in a rhombus. I think if you take, I think this argument of the hexagon, I think it's not going to necessarily be tessellated, where you see it nicely in the tessellation, but any polygon shape, I think, is integrable. And in fact, a circular one is also integrable. Just take the circle by itself, that's also integrable in the system. The circle by itself, that's also integrable in the system. It's somehow this combination of this regular polygon that you have and the circle that's giving rise to the calculation. Okay, so now, otherwise, what you can do to also make this calculation add, you could have added, you had this rectangular table, and then you had a circular over here. That's also chaotic, for example. Another way that you can imagine is that you take the rectangular table, and somewhere there's some sort of opening or something like that. There's an opening leading into a different piece of it, for example. This is slightly more interesting because you get this combination of an integral regional phase space where, as long as the particles moving along the rectangle, that's perfectly fine. But the moment it has entered the circular piece, then it's going to start moving to happen. So you get this interesting combination of chaotic regions of phase space and integral regions of space.
So, this rectangle is supposed to be integrated, right? So, let's say, you have 4 rays here. So, forget about the first 2 rays. Let's say we start from the 3rd ray, the one that's going at the end. Okay, and let's just say it's sitting just at the boundary, at the edge, just right here. And if you change the initial condition slightly, then we go somewhere else.
That's true. That is very true. So you can make special choices that will sort of exhibit the chaotic behavior. And that's why one needs to be a little bit careful. And of course, this choice of the here was to make it as dramatic as possible.
Yeah.
You could have chosen 2 particles that get sort of at the same tangent line, and then for a while they differentiate before the solid took into motion. But I think the way to think about it is as follows: if you so the number of points for which that case is going to be true is going to be much smaller than the generic case.
Exactly.
So you're asking about 2 generic choices of particles close to one another in phase space. You might find 1 or 2 exceptions, more than 1 exceptions to that rule. But for the generic choices of 2 conditions, you're asking one.
So, likewise, that case where you have a rectangle and then there is a circle. So, would you call that a chaotic system or not?
This one.
Yeah.
I would
Because it has a
not
similar-
call this a strictly chaotic system, because it's sort of, as I say, this one is a bit more interesting because you've got regions of phase space that exhibit integral motion, and regions of phase space that exhibit chaotic motion. So it was a bit more interesting to study. A lot harder as well. I'm not going into the details. Just want to sketch it as a possible choice one could find.
but for the purposes of what I want to discuss, which is classical chaos, I just want to illustrate this to highlight features of the chaotic system, ways to diagnose it, if you will. So, let me, I'm just going to leave a little bit of space here. And features of classical chaotic systems. One is the sensitivity to initial conditions that are sketched. So there's an exponential sensitivity to initial conditions. Exponential sensitivity. I'll give some more quantitative. It's just a second. Exponential sensitivity. That's the first. And secondly, there is this chronic behavior, but you can make that a little bit more precise, or at least I've seen in the literature that what people tend to prefer to use is the condition of mixing, which is a more stable probe for that. And the reason is the following. But you have in mind in mixing is not two particles that define the initial conditions. But you can imagine that the phase space isolates two regions of possible choices of initial conditions. So, a blob of initial conditions, if you want, and I'm going to take a second blob of initial conditions. Various choices. If I visualize phase space, I'm going to get this complete mixing between these initial conditions. They're going to be in a random position, random position and random momentum at the right time. And it's going to look like a complete mixture of these trajectories. And this, in a sense, overcomes exactly the difficulty that we can mention. That, well, you can have these two special choices that exhibit chaotic behavior. This way of phrasing it is stable, because you're not speaking out all the one initial conditions, you're picking out a bunch of initial conditions and asking, well, what's happening to that over time? And they will mix through the entire phase space. So it implies multiplicity, but not everywhere. I haven't seen very good counterexamples, but apparently this is one of mixing, but mixing does imply multiplicity. And that is the way of visualizing this terrible for all points of the phase space of all initial conditions. All right. So these are two conditions that quantify classical chaotic systems, or qualify them as classical chaotic systems, rather, not these two conditions. Exponential sensitivity to initial conditions, and the mixing of the choice of initial conditions. All right, so let me quantify this a little bit. I'm going to move to the board for this. So, the exponential sensitivity to initial conditions, you can quantify as I will have some choice of initial conditions, a big combination of position and momentum ordinance, as a function of time, ordinance, as a function. And I can compute its sensitivity by taking a derivative with respect to the initial conditions, some choice of initial conditions.
So, quick one, I just got a question. When you characterize these two conditions, 1 and 2, are these characterized independently or are these assigned at the end?
So there is some.
So, for example, they usually up and up exponent. I guess you get into for characterizing how the two vectors use each other. There's also a time scale for how long the mix it takes for the mixing to happen. Is that also characterized the same the up and up exponent, or are these separate things?
There are different. I think these are different time scales. So I'm not sure that there are general theorems that relate these guys. I think that. So it's it's essentially, as you said, the Apollo response, and I'm going to get to that. There's also the Ruel resonances. I'm not aware of the connection between those two time scales. But you will certainly have for chaotic system, you will have both. You will have both a set of vehicle exponents characterized by the exponential sensitivity to initial conditions, and a set of
the whole measurement system characterized the timescale associated with fixing it in the first place. Absolutely.
So I guess that's why the pre-body problem comes here, because even though your sensitive initial conditions, things are stable on a very long time scale. So there's no issue of us flying out of orbit.
No, absolutely, yeah, absolutely. So, yeah, there is, yeah, so typically when you think about the near-Earth experiments, I think it is usually a early time dependent one. So sort of early time behavior of the mechanic system, rather than late time behavior. So, yeah, as you said, late time things are going to be in this, always going to be in this random mixture of final position of the meter. So, yeah, so as I said, it's X, big X here refers to some combination of information of the data, and this is going to go like so. Well, I should actually use like. I can actually use actually. Let's start with goes in like and then probably a relation that you can see some coefficient called the Leopold exponent. And this characterizes the exponential sensitivity to initial conditions. I said that this is like, and when I mean like, I typically mean the largest Leopold exponent with respect to time that's going to dominate the behavior. The behavior, as you will see probably in the second picture, is really a sum over Leopold exponents. So you'll have lambda I plus t, and this is the spectrum of Leopold exponents dominated by the largest of these Leopold exponents. Now, the second quantity is related to taking thermal averages of these quantities. So if we define this, if I take, and yeah, I should credit the online lecture by Stanford on many details and goals. If I want to take a thermal average of these quantities, then you're going to integrate with the phase space. You're going to have e to the minus beta Hamiltonian and some function of phase space line over the integral of phase space of e to the minus h. And this is a quantity that you can compute. You want to take this, call it the thermal multiplication value of some function of phase space coordinates. And a particular very simple one that you can of course consider is the just the phase space coordinates, so just x. Okay. So you can consider the correlator x of t is 0. Take this integral of the phase space coordinates, subtract off the disconnected part, and this is going to give you something related to the Ruel analysis. So you're going to sum of I, ei, e to the minus mu I times t. And what this is communicating to you is that the correlated between two different choices, or particle and its length time behavior, and length time this is going to decrease exponentially. So it's going to go to 0. This is particle and its length time behavior, and length time this is going to decrease exponentially. So it's going to go to 0. This is communicating this random configuration that you have. In the first place. And these are called Ruel distances. And the reason that they're related to time scale, just to make it completely clear, is of course because there's a factor of t associated with these quantities. So that's why the Leopold exponent gives you a time scale which there's this exponential growth or exponential divergence of initial conditions, and there's another time scale here where this complementary starts vanishing.
Should we worry about units on the left-hand side?
That's a question.
Should we worry about units on the left-hand side? Looks like there's x squared minus x.
Oh, you're right.
Looks like there's x squared minus x.
Oh, you're right. There is a square.
Square.
Yeah, absolutely. Thanks for that. Yeah, and what this is essentially communicating is how long before the system starts forgetting its initial conditions. Pretty close to like the initial condition. Now, this is as far as I'm going to go into one can
consider, but what I really want to do is get to quantum fields, notional quantum fields. So let's insert that quantum fields. Now, there's an immediate difficulty that you may pick up when it comes to quantum fields, and that is that both of these notions that we use to characterize classical chaotic systems relies on phase space. It relies on position and momentum. Of course, if I go to a quantum mechanical description, we've got the high principle. I can't pick the position that momentum of a particle out of the position, as there's also going to be an
The explanation sensitivity to initial conditions and the sensitivity.
So I believe so. So there are cases where you can, as far as I know, that these conditions do not have in hand. For a chaotic system, you will see both these features. And I base this purely on the system's motivation because it's just a system that we study. So systems that have issues with chaotic or solve on a computer or some of these issues, they do identify both of these. But I'm not aware of the theorem linking the two. If you had a theorem, then you would also be able to probably make a statement between the real part exponents and the relativism. It's some connection between those two timescales, which seems reasonable, but I'm not aware of it. As far as I'm aware, those are two different timescales. Theoretically, you expect to see both.
Some people distinguish between non-integrable and chaotic. It's not supposed to be exactly the same thing.
Yes, absolutely.
I'm not too sure now what the different, and if you can quantify the difference.
I think there are many reasons, many ways in which a system can become non-integrable but not yet chaotic. I think it is related. So first, so what you can imagine is that this mixing curve, so that you still get this soup of different outcomes of the initial sorts of conditions, but it's not completely mixed. You still get, bigger comoids of the initial conditions, for example. I would imagine it's something like that. That's one way where it could break down. In the case of the initial conditions, that there's maybe not all the one, but maybe a larger choice of initial conditions. But for the majority of choices in phase space, you'll still get this exponential divergence in the past, but you'll get some non-trivial subset of them for which you will still get big sort of information.
Yeah, good. So I'm assuming the Ruel exponents there for a chaotic system would always be positive, right?
That's right, yeah, absolutely. Absolutely, that would definitely be positive because you want the system to forget its initial conditions, exactly. If you pick up a positive or a negative one, then that's an indication that you're not the chaotic system. All right, thanks. Okay, so what I've sketched out is this classical chaotic systems, and I've highlighted one of the main difficulties with quantifying a quantum chaotic system being that both of these rely on space, which is a difficult notion if you go to a quantum mechanical setting. But there is one way, there are a number of ways that I will sketch that I can think about a quantum chaotic system. I should add that this is not unique. It seems that this is still a field of research. What is the best way to go about a quantum chaotic system? One way that you can imagine is that, well, if I just treat it semi-classically, well, then I have a chance of still covering some phase description. And in fact, that's exactly the first thing that I'm going to introduce. So there's a semi-classical way we want to think about these trajectories that takes up nicely with the quantum mechanical picture. What it's essentially based on is the particle formulation. Think of particles, as the probabilities being related to trajectories, all possible trajectories being weighted by an action. And what you can write down is the semi-classical wave function based on this. So this is, I think this is essentially the WKB approximation, but I could be wrong. That could be, I think this is essentially it. Then you have a semi-classical wave function. I could be wrong. That could be, I think this is essentially it. Then you have a semi-classical wave function, where what I can have is e to the I
It's classical thinking of maybe just adding here. Here you'll have some final position and time. Here you'll have action that's dependent on the final position, initial condition, time over h1. And then you have an initial wave function, q prime and 0. And then there's some weight factor in front, just to normalize things slightly. That factor turns out to be square root of the determinant, the derivative of q prime with respect to q, and square root of this. Okay, now this is an expression you can write down. This is a semi-classical approximation to the wave function. The main assumption here is that you have a final position and an initial position, and you have some action weight in that. Multiple parts. So this is true at very short times when you have an initial and final position. That's there's only a single classical action that takes you between those points. But at longer times, you can have multiple parts. So the problem now is, well, when I'm computing this determinant here, there can be an associated sign associated with this. It's called the Maslow index. So I can have different parts where the determinant of G, Q, prime, or Q, for part J.
Sorry, could you read the integrating of the initial positions here?
So this is not the propagator of this one. I think this is the WKU approximation for the I might have missed the integral.
Yeah, this is like a saddle point, and the saddle point is your cross connection.
So I don't think this is integral necessarily. Of course, I copied from another text, so I may have missed it, but I don't think so. I think this is just a saddle point of the. Without if you have multiple saddle points, then there's an associated sign difference. So e to the minus what's called the Maslow index. I think it's the minus pi of the Maslow index, J of Q of Q. The Maslow index is related to how the corporate parts crossing placements. So the details here aren't too important for all purposes. And now what you just need to do is sum over, so the great expression is to sum over J of these different parts. You'll get a particular determinant. So I'm just going to do the absolute value of J, and you'll also get this Maslow index coming into the picture. Maslow index that depends on these. Okay. Now, what you can do from this, there's a number of references. I'm not sure if I put them on the website, but I'll be sure to do that. That goes through this derivation in some detail. It gets technical, so I'm going to skip over most of that. But the key part is that, like I did for the wave function over here, you can also get a classical expression for propagator. So a semi-classical expression for propagator. Essentially, it is of the same form. The only difference is this weight factor is different. That's weight in parts. One other feature that's important for the semi-classical propagator is that it doesn't quite satisfy the condition that propagating from point 1 to 2, and from 2 to 3, integrating over the points 2, it's not the same propagator from 1 to 3. There's an additional condition you need to impose on a semi-classical propagator, and that condition boils down to the fact that your paths must always be smooth in the semi-classical. Always exclude parts that you're describing. For the propagator, you can have the Green's function. So the Green's function just as a reminder, some stability. It's given by, again, we're going to have, actually, I'm going to skip the specific expression, but it's going to be very similar. We're always going to get this phase feature, this phase, the classical action, and the Maslow index appearing here. And to get them, you will take an integral of the propagator. So e to the I, e t over h, or function of the propagator, q
Okay, so now you've got this expression. You can put this as the semi-classical parts. The semi-classical parts, of course, once you can visualize nicely, it's sort of replacement as well. Position, it's time dependent, but now the point is that what you're going to ask is for the next bit that I want to get to is you're going to get all these different parts. There's some over XJ, so there's sort of pairs of parts that you need to take care of when I'm computing correlators. So specifically, the quantity that we'll be interested in is the density of states. So the density of states. The density of states is going to be related to taking an integral of Q of G at a particular energy, and also the diagonal matrix of it, E plus epsilon multiplied by G Q E minus I epsilon. And then ultimately the quantity that you're interested in computing is K of T, which is given as a particular correlator of rho of E plus epsilon over 2, rho of E minus epsilon over 2 over rho. Integrate with this change in the E all the way I so these expressions, as I said, quite long and getting to look at it quite technical, but I just want to pause and just highlight the key features of this. In the semi-classical description, I've got some classification. There's also this additional Naslov index that you need to take count on, and that's related to sign changes in this Jacobian for different paths connecting these two different pieces in placements. So you've got this phase piece over here. The quantity that you're interested in is, as a product of two of these guys, and you want to take this correlator. So what you're interested in ultimately is, sorry, this should be a minus, this should be a minus. I was going to say two, it has to be pairs of parts. To get this, so rho here is sum of two different pieces containing an exponential of different parts. And then you're taking some correlator of two of these. So in this correlator, what's happening is you're considering pairs of classical trajectories in phase. This is what this quantity is putting together in some way, and that you're computing. So this is a classical quantity depending on pairs of classical trajectories. That's the key bit. So this quantity seems quite well, primarily because it didn't go through the default calculations. But as I said, I will be proposing some references on the website so we can go for itself. I don't want to go down there any too much. It's a bit technical. But nonetheless, what you see in that quantity is of the duties. And
Do these trajectories start and end at the same point?
yes, that's right, exactly. So in fact, there must be smooth, so that's the one condition that I just highlighted. There must be smooth parts. You're considering this, and what it turns out, because you're considering the diagonal piece, you're considering periodic orbits. So what's contributing in this case, in fact, you're considering periodic orbits that are smooth in this case. Those are the pieces that you will sum up in this case. Now the question you can ask is, okay, before I get to that, so I think that's very just important to highlight smooth parts, in place space, and then periodic orbits. Always periodic orbits. And for that correlator, you're going to study pairs of correlators of periodic orbits. So a correlator involves periodic orbit 1, periodic orbit 2, periodic 1, periodic 2. I'm going to get to a statement regarding this in a moment. Before I do that, I should just maybe highlight this connection to quantum codes. And there's a famous conjecture by Norwegian's Gianni Schmidt, VGS conjecture, that states that for a classical chaotic system that is now quantized, that K of T has a very particular form, depending on the symmetries, the time reversal symmetries of the problem. So if you have no time reversal symmetry in the problem, then K of T should just be. If there is time reversal symmetry, and the time reversal operator squares to 1, then it should be 2 tau minus tau log 1 plus 2 tau. And if there is time reversal symmetry and it squares to minus 1, so think of fermions, for example, then you'll have a half tau minus a quarter tau log 1 minus tau. So this is the VGS projection. And this makes a very nice connection between semi-classical orbits and what you expect for a chaotic system that you can quantize.
I'm sure you could repeat if what happens with the classical code.
Yeah, for a classical chaotic system that you quantized, you compute K of T. So you're thinking, because this is all in the semi-classical description. So you've now quantized your system and you compute that quantity K of T on the right. Then the statement is, according to the VGS conjecture, that K of T must be one of these 3 forms, depending on the time reversal symmetry. No time reversal symmetry, tau squared is 1. Time reversal symmetry, tau squared is minus 1.
Are we talking about one system, 3 systems, that doesn't matter?
Doesn't matter.
Any number of resistive, like everything would have these processes.
I think the projection is that it should hold for any chaotic system. I'll give some flavor as to why this works based on semi-classical forms. Now, there's actually a really nice understanding of this semi-classical picture by now. And the understanding goes as follows. Not going to read that anymore. So as I said, what's contributing in that correlator that we have is pairs of orbits. So pairs of periodic smooth orbits that we have. And you can ask a question, well, what's the leading order contribution to that? So I'd take H bar to be really small, get a stationary phase approximation, and then ask, well, what's the leading order contribution to that? What parts contribute to that? The parts that contribute to it are pairs of parts of periodic orbits that exactly cancel each other in a certain sense. So think of something like elliptical orbit. Here's orbit 1. Semi-classical smooth in a certain sense. So think of something like elliptical orbit. Here's orbit 1. Semi-classical smooth orbit. The paired of orbit traces up exactly the same path, but in the opposite direction. This is the leading order approximation in that 2 ways. So this is if this is the leading order in H bar. So you're making expansion in H bar using the stationary phase approximation. This is a contribution to the leading order. You can of course have a different periodic path, something like this maybe. And it turns out exactly the opposite direction. And so what you're relying on for this proof is that since it's a chaotic system, all paths are possible. So that's the input of this for the chaotic stuff that's going in. There's this ergodic filling of the phase space, all paths are possible. So you sum up all of these different paths, and you indeed reproduce the leading order contribution in I should add here that this tau is measured in the this is measured in units of something related to H bar. I forget the details of it, but it's essentially related to its measurements of something related to H bar. So that's why you can make a tau expansion and compare a tau expansion to H bar expansion. Yes. Okay, so this was for a long time the extent of the understanding of this conjecture that it could be semi-classical parts, leading order contributions and cancellation. But of course, these are more involved functions of tau. So we cannot make a statement beyond the leading order. And indeed, you can. There was a beautiful insight by Siebert and Rechter, where they realized what the subleading corrections to that is. They realized the subleading corrections, it was very shortly to getting the whole series of subleading corrections that you can sum up, and you effectively produce exactly these expressions for the associated unrelated symmetries. What's important is that it's not a proof of the BGS conjecture, because it's relies on taking a semi-classical limit. So when you're stating that all of this must occur before a particular time scale, before the semi-classical limit starts breaking down. Beyond that time scale, most of it can be made, but before that, it's well understood where this comes down, where this comes from. And the subleading paths to this are actually, what you need to do is you consider paths that are really close to, or that have an interaction region that's really, really thin. So like this path. And its payload path has the same shape. But at this interaction region, it actually crosses once. So if you don't get paths that cancel exactly, it will cancel in one half of this. So you go here, go through this cross region, this direction, here, here. And so and this part of here continues in this direction. So in this part of it, go in the opposite direction, but here they go in the same direction. This is the first order correction. This was done by Siebert and they reproduced the correct subleading behavior of this function type. And this was extended later by just put a reference here, Miller and company. And they did this series of papers quickly. One nice one in that series is this one here, 0503052. Miller where they describe, inspired by Siebert, all the subleading corrections. And it's all related to the number of interaction points. So here you have a single interaction point with these two paths, and then the region where the one crosses, one does not cross. But you can write down ones where there are 2 interactions, 3 interactions, and so on. And if you sum up that whole series, you can produce exactly this expression. And as I said, this is it's a really nice handle on why this works. But the one portion is that it's not a proof of the BGS conjecture because it requires that the classical relaxation times, the classical time scales, when you're dealing with a dynamic system, so here you should have in mind those Corral resonances, Leopold exponents. These are the classical ones for your classical system. These time scales need to be much smaller than the so-called Ehrenfest time. The Ehrenfest time, the Ehrenfest time is measuring for you how far can you trust the semi-classical approximations. So not the so and it's related to log of some constant over h bar. So these time scales need to be much smaller than the Ehrenfest time for this argument to go through. Beyond that, it's not how this works, but at least in this regime, there's a very important why that's a function concept. All right. Is this a good point to take a break, or should we be looking for
15 minutes? So maybe it's good time.
yeah, that's right.
take a slightly shorter break than maybe 20 minutes or so.
That sounds good to me. This is about halfway.
Yeah.
Okay, perfect. Are there any questions before we,
I can get why someone would think this is a proof of BTS. Like it is not like
That's right.
but
So-
why would someone think that?
No, it's just that people use this function, all the time. So you might be, because of that, you might think that, okay, well, because of what you're doing with the towers and derivative expansion, it's, but as I say, it's, the key thing is that this time scale thing is important. I remember the first time I read through the papers, I thought, oh, well, they've proven this, no, it's only proven in this regime of time, so for short time scale.
The BTS can get true for short time scales.
So it's been, I think the BGS conjecture is conjecture to hold for any classical chaotic system that you've processed. And this, so you've got this evidence that's sort of based on really short time scales, but you've also got a lot of numerical evidence, systems that can that study where it does hold, even beyond this. So I think the idea is that this should hold
Were you using this exclusively? Just as a matrix model or something?
Sorry.
Were you using this exclusively? Did you still use a matrix model or something?
I am not sure, unfortunately. I haven't seen this really myself. I've just seen from other talks that people have given that there is a substantial. I haven't looked into that myself, unfortunately. I've just seen from other talks that people have given that there is a substantial. I haven't looked into that myself, unfortunately. The one thing I should maybe add as a spoiler for the next session is that, so based on this, you would say that so we've still not yet addressed what is spontaneous. I'm just sort of giving you this connection between the semi-classical description and systems like classical chaotic that we quantized. There's this really nice connection. So one would say that, well, based on this, we could make some conjecture for what the system is. Which we'll get to in the next lecture, but I should add that that is one possible approach. And we're going to be looking for some other approaches as well. So different things that one can say that this is what I define what it has to be. But there's always a good check. Whatever measure you choose as your measure of chaos, if the system according to this matches, so say you have to give me the system, you compute this quantity, correlation function, and it turns out this is the form. Then the BGS conjecture tells you, well, this is a classical chaotic system. So your measure should be the positive diagnostic. Yeah, that's
One more question regarding this.
Sure, sure.
You're quantizing a classical system. There's no unique to quantize. Are these statements independent of that?
Oh,
Any way to quantize one of these same issues?
That's an excellent question, Vish. The first one answer is I'm not sure. My suspicion would be that I think it would be sensitive. I think that's probably also another reason why this should be seen as a proof of it, because it provides a particular scheme of quantum system.
The electric time is again what? Is that defined the BTS?
So the Euclid's time is essentially, so there's no, you need to look at the specific, it's always related to H bar, so it's always related to H bar. It's H bar and then a number related to the quantum numbers of the system, typically large quantum numbers of the system. But I don't think it's been made extremely precise. I know there is a difference in that time scale for chaotic versus integrable systems. If I recall correctly, this logarithmic behavior is chaotic systems, whereas for integrable systems, even this time is longer. So even this time, one of H1 or something like that. It should scale like But it's going to be dependent, the exact ratio is going to be dependent on what numbers of the system.
I just mean like the definition of it. Isn't it supposed to be the time until when BGS holds?
Oh, so the unit time is until the correspondence principle is valid. That's what if I call it. That's the definition. So in other words, the semi-classical is works out essentially.
Yeah, so if BGS is true, then this is supposed to be valid, like this is supposed to be.
Oh, that's so you're asking if the BGS conjecture is true of this. I don't think it implies that necessarily. I think the BGS conjecture is motivated firstly by this and empirical studies, but I don't think it has a statement on the unit stuff. Oh, yes. That's a good point. So certainly in a chaotic system there should be scrambling, but you can have scrambling without chaos. I don't know. In a system there should be scrambling, but you can have scrambling without chaos. I don't know. But certainly chaos does imply scrambling. My question is this just chaotic? Is this scrambling? I'm not sure.
So isn't scrambling like PC scrambling in a long time range, and the chaos can be detected in the early times?
Yes, I think that. So scrambling is something that you expect to longer time scale than this. Yeah, okay, maybe let's say that's good point. So this will not be the argument related to scrambling, because you're not in the right time scale. Yeah, that's a good point.
Okay, there's no immediate questions. Let's have a conference. Let's do next door. I think you can leave your stuff here. We'll be watching the space during lunch. Let's have a little
Oh, so we're going to get into random So at the heart of it is that quantum chaotic systems should have the same spectrum as, in fact, it's very closely related to the BGS condition. That's the starting point of all the exactly that. So you have for each of these traits,
Yeah.
this is actually the, I think this is related to the, all the different matrix models. I think it's something like, this is the orthogonal, no, this is unitary orthogonal simplicity. Oh, that's very close to that.
Yeah. Because there is a thing that came not too long, I mean, a few years ago. Sorry, do you want to ask a question? No. On counting problems related to quantum chaos by Orlov and the Russian guys, and it involved previous numbers, matrix models. And actually that's why I'm interested in
See,
yeah. So anyway, I'll just wait for you to.
yeah, sure. I don't have a lot of detail to say on that.
Yes.
That's roughly the extent of it. The other thing is, of course, this spectral form factor that's closely related. So it's about the spectral statistics of the
Okay.
of locality model.
All right.
And the spectral statistics that it should satisfy is that's really what this boils down to. That's related to the spectral statistics of particular random matrix.
Okay.
All right.
Well, that's good. Yaku, is mixed scrambling not related to the system's ability to forget information?
Yes, that's right. Exactly. So that would be
Because that scrambling is that somehow the initial condition is still contagious. Not,
absolutely, yeah. So that's why this is a statement. This group, these are well businesses are exactly what I'm describing. Exactly that. So as you say, for kids initiated initial conditions.
When we speak of scrambling, are we speaking about some kind of fuzziness of the system, or those are different notions?
Well, what do you mean by fuzziness here? So like,
Because if you, okay, what do you know exactly how to formulate it? You mentioned, the transition from the classical to the quantum, and somehow, one of the things that you mentioned, prompted me to ask that perhaps actually the right formulation was what Hector mentioned in terms of the scrambling, rather than not maybe the fuzziness, of the system. So I think, yeah, that's more the correct term. Are you going to speak about that as well?
Now, just so this is so this is a motivation for what? So we've discussed this feature of system. So this gives you a handle on.
Yeah. Maybe you want to.
yeah,
Sure, yeah,
I
I
can
just
you guys, I
wanna-
was
Yeah, we can just.
you wanna-
I just want to reform this into this actually.
Oh, yeah, the three.
Yeah, so this is going to be for the matrix models. Just to mention this.
Oh, okay, right. So that's two questions. By the way, paper that knows.
Okay, thanks.
Green theory, orthogonal, and symplectic.
That's right. So it's I've made the footnote of that. If I recall correctly, that's the one.
So the one that we apply to the previous numbers would be the first one. The first one is when you consider.
That's the one.
Yeah, sure.
Right.
I already had.
You need
Yeah.
this one.
No, just now.
There.
Yeah, I just had a
Oh,
short.
you're recharging this. Did you
Yeah,
stop
it had shut off,
Oh.
so I'm trying to check how far did it go? Is it the battery? I get the feeling the battery's not able to hold much charging.
It's a bit obvious, because you almost never got used. Yeah.
Yeah. Because right now I put on a charger and then it's got 3 bars. But then when I switched it on after I finished talking, it said low battery. So I get the feeling we're in that life of the battery. Maybe after the session maybe I could get those disposable batteries just for a week.
Oh,
Yeah, just to replace this one for now.
Oh, okay.
So you could get-
Where would you get them?
Just clicks.
Oh, okay.
Because just a
How
regular
small?
AAA.
No, I think it's a smaller one. It looks smaller than a AAA. Or am I?
Yeah.
Oh, it's AAA? Oh, okay. Oh,
Because that's what I use for my mouse.
Oh, fine, okay.
So we could quickly, buy a set and then if one runs out and then we just replenish. Although I'm not sure how to resume the recording, hopefully without erasing.
No, but if you stop it, you stopped it, right? So you
Yes.
just stop it. Oh, I think it's gonna start a new record, because the recording was timestamped.
Right.
Yeah, the second, like the other one was 001.
Oh,
One you
got
saved
it.
is 002, so I think.
Okay.
I'm gonna quickly check.
Knowledge. Recording time for 3 hours. I'm wondering if I could quickly go home to pick up the money.
You have to remember the screen.
I don't know, that might be a bit of a stretch right now. Is that going to come through? Or?
I hope so. He said it's coming on the garden.
Okay.
18 megabytes. Hope doesn't.
Recording on 192 kbps. Right. Charge for now. And what's the audio pickup for the stream?
Just low, okay, when I put the headphones, because I don't have to use that for big, right? With the headphones, it's actually clear.
Okay.
Not that voice.
And what mic are you using?
Just the mic.
Really? That's nice and well.
There's one toilet that you go out to the left, just right on the right, but up the stairs. Sorry, just checking. Yeah, I'm afraid it's only probably 13 minutes. Yeah, so probably needs. It's a bit low, but it doesn't sound like bad, but I mean, it's low but really enhanced.
Okay.
But yeah, it's only 13 minutes.
Oh.
So you're right, yeah, that's cool.
You don't usually get battery line up.
Because
You present to us.
we could roll slow now.
Consistent.
You have so many on the phone, but yeah, basically. One? Yeah. Because you have your own.
Yeah, it's been working.
Some.
Yeah, great. I've got for a second hour. Perfect, yes. All right, so I actually got a question right now that reminded me of a note I made with things on this automation. But that is really insightful and important. That is that the quantity on computers is the scale of T, and what's related to can be related to classical forms. The formula there is known as the Birdsmuller trace formula. But then this one previous statement on the BGS conjecture, giving a specific formula like the time reversal spectrum. What I should have added here is that what the BGS conjecture really is a statement about the spectral statistics of the problem. What it is here is the density of states, and the spectral statistics here are exactly those we would obtain from a random matrix theory. And the random matrix theory is responsible for it in this case is here's the unitary theory, unitary random matrix theory. Here is the orthogonal, and here is the symmetry. So you can compute this quantity for these theories and you will obtain these ones. So the BGS conjecture is a strong statement about the universality of quantum counting systems. You can take any counting system you want, and then the spectral statistics must be at late times or must be it must have forgotten its initial conditions, because that's difficult to solve. It must be of these particular forms.
So didn't you say that the first case was when we had no timetable sets in?
That's right, yes.
So how does that correspond to unitary case?
Oh, yeah. I would have to do this to play with my hand remember off the top of my head how that works exactly. One other reference that I have so there's a really good reference. I think that paper by Willard people that I had in the first year. That gives a good unpacking of this point. What I really just wanted to use this for is a statement of that the spectral statistics of chaotic systems seems to be a good thing that one can take to the quantum realm. That's something one can do quantum mechanics without issue. And not rely on the semi-classical approach. So based on this, one thing one might want to study is the so-called spectral form function. So this lecture I'm going to be dealing through specifically two notions of chaos, two diagnostics that we use and motivate them, and what's the sort of expected behavior that one can get, building towards complexity at the end of this lecture, and it will dig details of complexity in the ways of computing it and so forth in the third and fourth lecture. But okay, so the first diagnostic I want to introduce is the spectral form factor, and it's heavily motivated by this ETH contribution. So it's a statement about the spectrums of distance of these different points. How this is defined is the spectral form factor. Maybe I can use this F. It's equal to, it's essentially a sum over the energies. So I'm going to take in and in, e to the minus e in plus in times time dependency of e to the minus e in minus e. Divided by sum over beta, so that's just a tissue function squared. I just have this as the squared.
Yeah, it should be square, otherwise it's not symmetric.
Yeah, you're right. I must have write down everything in my notes. All right. Now,
Finding the numerator,
numerator.
it doesn't seem symmetrical in the
Oh, you're right. Well, so you've taken, so the decision is you've taken the sum, you've taken its complex conjugate, the sum over n, e over n, and you've taken it multiplied by its complex conjugates to be the real quantity. Right?
Yeah.
I think that's right.
Yeah.
That's right. And, so this is what it is, you can confuse. Maybe just to contrast this with chaotic systems, let's just plug in a simple quantum mechanical system and see what it does. So let's take the harmonic oscillator. The harmonic oscillator, well, the eigenenergies are of course given by omega n plus half. Right. So this is something that you can just plug into this definition here. You get some geometric series and you sum over. But what you can up with is then this SSF for the harmonic oscillator. Is given by over 2 cosine of the vol omega times beta minus cos of omega t. In this some normalization at the front, but it's not too important for purposes. I'm going to not using indices or not using the scale, and just get the schematic sketch of this. So what you have as a function of time, I'm sketching this is, and I'm just going to make a cutoff here at pi over omega. Then you have the maximal value that this obtains, which is essentially the partition function squared. And there's another cutoff that's important, that's z of 2 beta. And the spherical form factor for the harmonic oscillator is basically of this. This starts this cuts through this point and then goes on. And the reason I've pointed out this time over here is that after that time you've got unitary time evolution. So then it will again start to rise, and after the time 2 pi over omega, the whole system is going to repeat. So that's the form of this form factor. And of course, I've chosen some value of beta, but this is just a schematic sketch of what you can expect to see from this. So, of course, for one oscillator, it's an integrable system, exactly solvable. This is what you see. But now, generically, what you'd expect for a chaotic system. This is from a famous paper by Stanford, which before that, I see on my own proportion. But I'll be sure to post it on the website. The argument basically goes as follows: that well, at short times, this factor over here is just from the fact that well, you've got t is equal to 0, you define it by this function. Maybe there's no official function that I'll make for our purposes. The point is that this is the value that starts off from, and this you can expect from anything. This is just that at short times. It's going to be about z squared. But now what you would expect at late times for a chaotic system is that the energies are essentially like they're of random matrix models. So they should, in the sense, their contributions at late times should average to 0 unless Em is equal to Em. So that is at least the schematic argument. So it should roughly end at the value Z. So we know that at early times, and this is the behavior, and at late times for a chaotic model, it should be around here, at some values into the 2 meter. I should add here that what they find in these chaotic systems is that, of course, it's an oscillatory function with some fluctuations at times, and they typically need to perform some averaging over some coupling constant or something like this.
Might have to actually be vector form.
Sorry?
It needs to be actually vector form.
So it's essentially just a so it's just so in this way it's a function of the eigenenergies of the system. We're going to use this as a way to diagnose chaotic systems. So it's of course not it's only motivated by this, but notice that from the semi-classical algorithm, one saw that the spectral statistics are that we have the matrix field. So based on that, one can conjecture that quantities that depending on the energies of the system can be a diagnostic of the curves. So that is why this is introduced. So here, so let me just. So this is a region, like I said, where it's averages to this 2 beta. Now, right. Yeah. And so one of the typical examples of this is SYK, for example. SYK, you have a random coupling J, and this is obtained from averaging of that coupling J. So what they would do in that system is they would numerically solve for the spectrum at some fixed choice of J, and get a particular answer. Well, let me maybe, before I do that, I'll maybe just sketch what and get a particular answer. Well, let me maybe, before I do that, I'll maybe just sketch what the proposed idea for or the conjecture is for a system. We know that this is late times, this is early times. So what I know from studies of the systems is that, and based on those observations, this is the expected form of the spectral profile. Very cartoonish, which I'll explain in a second why that is the case. But you have these key features that are called slope. You have this plateau region at daytime that is due to basically those off-diagonal terms that should cancel off the averaging, and you've got this ramp feature. And this ramp feature, if you compare with what we had in the oscillator, is quite different. This ramp feature is one of the key things that people look for when they're studying form factors of systems. One example of this is where the S1K model is done. So the S1K model, we've got a battalion. It's essentially a full Fermi complex. Sign I, sign J, why you want it? Sign K, sign L. With some coupling J, I, J, J. I should actually look at the same I, J, L. And you solve all of this. Now, and you have some in number of species, in number of species. Of these fermions, and you have some coupling. Now, the way to treat it is like a model. You get analytic answers if you average over these couplings. So you visualize these couplings as being random, typically chosen from a Gaussian ensemble, and you average over them afterwards to get analytic answers for all sorts of quantities. The points of the spectral form factor, this was a project by Dr. Stanford and the collaborators. You can, of course, solve this numerically, because what you can do is pick some value of J, some fixed value of J, so some matrix choice for it. You can analyze that numerically, get an answer for the spectrum. And you can't do it for very large n. Recall correctly that n is equal to 40 or 15, something like those lines, but you can get an exact answer out. And you take the spectral form factor, it has a generic form of following a slope point nicely, but at the ramp you get these big fluctuations occur for a fixed value of J. Right. So you still get this ramp feature, but for a particular choice of J, you don't get this nice flat plateau with J times. In order to get this plateau, you have to average it. Yeah, exactly. So you have to pick an ensemble of choices of J, and take an average value of this afterwards in order to get this plateau feature. And the expectation is that in a chaotic system, this ramp is really the feature that you're looking for to diagnose it, but you should get the plateau if appropriate averaging, appropriate averaging generically, but certainly in the S1K model, this is what you would have. All right. There are, as I said, S1K, or the spectral form factor, is based on the spectral statistics of mathematics theory as some basis. There are a few references that I've put out that want to compute where the spectral form factor can be computed, relations can be drawn between spectral form factors in different systems. But what I really want to focus on in this lecture is the untimely correlator. Very instructive application for us to work on. Before I move on to that, are there any questions on the spectral form factor? Great. So it's this is sort of the first time I've seen it in my own, first time. I know the diagnostic itself corrects is goes back quite a few decades, so this has been used for quite some time. But what I want to focus on in this lecture is the out-of-time correlator, which is another diagnostic.
So the overall statement, okay, there you wrote the harmonic oscillator, right? And just died, just dies. Dies. And what we're looking for is whether it's resurrected somehow. And absolutely, and there you know that it's not.
Exactly, and it's based on the fact that it must resurrect because it's, even in the case of the harmonic oscillator, it dips below this value. And for a chaotic system, it must plateau at this value at all times. At least
but does it have to go down the ramp or?
It could also do this.
Okay, so that's specific for S1K.
This is specific for, well, I know the explicit results of S1K. This is conjecture to be true for more generic systems, but I think the jury is still out to be in that list.
That's not the real quantifier, whether it reaches plateau at Z of 2 beta or not. I mean,
absolutely.
How it gets there is not so important.
Yeah, the issue with the plateau is that if you're studying a particular system, there are many fluctuations, so it's hard to identify the plateau in the data. That's the issue. So even if it is S1K, which is, I think, one of the good analytic handle on, you have to do that average in order to see the plateau. So if you were to look at the spectral form factor as your diagnostic, then probably this region is going to be very hard to see it later. You do know that it must ramp up, which is not, for example, on cost. So that's why the ramp is typically looked at as a way to extract that information from where it's going to come out. But certainly, the appropriate averaging, as they say, is the two, but that's fine. What's the appropriate averaging? So it's not good for what you're doing.
So I have two questions. First is, am I correct in thinking that people just look for the ramp without knowing that it will blow up because of that negative beta that will like sort of kill it if it's trying to blow up?
Oh, so remember that you're picking this some fixed value. There's some fixed value. There's some choice of beta. So
Yeah, I mean that term will not let it go in.
yeah, we choose a fixed beta. It'll have some constant. So we won't block it like that.
Yeah, and the second one is, if, as you said that the spectral form factor could just go insaturated or plateau at Z2 beta. In that case, we don't have any ramp.
Yeah.
So how do you know that a particular model that you're looking at will have a ramp or not? So basically, like, as you said, that ramp is the feature that people look for in absolute, right? What happens in those cases?
So in cases where it just flags, then it dips below the
Yeah.
value. I'm not sure, actually. I think that's actually a problematic case. I think, so certainly when I put it down with the harmonic oscillator, this was a function of beta as well, on the concrete. A function of beta and omega, how big or how, so the concrete, there are examples where it also does that. So I think you would have to tune beta and omega appropriately.
If I may, I think, Nathan, so like one can think of the SFF as having a connected and a disconnected part, and the disconnected part dominates at early times, the connected part at late times. So what you see in that characteristic shape is a slope which actually decays to zero from the connected part, and the disconnected part gives you something that ramps the plateau. So the shape you're seeing is actually the sum of two contributions, which are, and that's why you're seeing this.
So why is that second part zero for a literal probability?
I'm not sure.
But that's the statement, that for the harmonic oscillator for the disconnected part of the stage,
I would least that it would have to be related to, there should be an equivalent statement to the off-diagonal terms and that times sum that not contribute. So that's how you model for the plateau. And the growth must be related to that somehow.
Also, when I'm speaking about disconnected,
So that's how you model for the plateau. And the growth must be related to that somehow.
also when I'm speaking about disconnected or connected, so you're taking an average actually of its order, and it's either you're averaging Z together, sort of separately. So that's the sense in which it's disconnected. In the harmonic oscillator case, it's a bit different because I suppose I'm talking about an S like H is sort of the new one. For the harmonic oscillator, I'm not exactly sure that runs on play in terms of connected.
And just the final point, we'll always have that plateau below Z2 beta in case of integrated systems.
Oh, I don't think so. I think even when I put it up there, I also like the cases where we didn't quite do that. So this is for, I think at the beginning there was some cutoff where if you chose mega too big, wouldn't fit completely below. No, actually, bigger mega is good. Also small mega, where you would want to below. Because you've got this time scale where you'll have to start going through the motion. And I think you had to make sure that there was long enough time for the decay to be small one. So this is this is again a pretty selective choice. Unfortunately, but yeah, well, the point is that this is what you're ultimately looking for is the ramp. I suppose the ramp might be a feature of certain choices of parameters. Because you could have this behavior, I think that could be very problematic. I haven't seen that addressed in the literature. Because, as I say, the ramp is very good thing below that. I suppose the expectation is that for a chaotic system that explores enough, or it's only going to be periodic after a long time scale probably, so it should decay below the chaotic system. Predictable system where the time scales can be short, or it might not be.
So I think it's characterized the time scale where you get the minimum and start ramp.
Oh, yes. So there's ramp time that, so I don't think what is the ramp time. I'll have to revisit the calculation. I think they do give some idea of what the time scale is, but.
Through this time, yeah. Through this time, through time.
Yeah, like there are a few time scales. There is errand fetch time, there is storage time, and a couple more time scales. One of those.
One of those.
So there's like a big paper for that program.
Yeah, and that's separate, actually. Well, I haven't read the whole thing.
Yeah, I think there they give some kind of estimation for interpretation. Yeah, I think there they give some kind of estimation for interpretation through this time like that. So
But, so, as I said, this is one possible diagnostic. Another diagnostic that's, I think is more prevalent in the literature. I've seen it in many, time-time correlation. Now, the time correlation is inspired by what we saw earlier in a classic economic system. You have this exponential dependence on the initial functions. And you remember that it was essentially Px of t. These are phase space coordinates. And these grow as dB of points, right? So some constants times respect to the area of points. Now, what you can consider is, of course, if I square this, then I'll get another expression depending on the ability exponents. You can take a Poisson bracket, when I go to the quantum mechanical picture, this becomes a commutator. So that, I'm not going to go for the details of that, but that's at least the motivation of it. As I came up with this quantity that you that's called the double commutator expectation. And even though we started with x and x0, the claim is that it should be true for generic functions of phase space. So the quantum mechanical language, here would be that you take a generic operators and compute this expectation. And that this should give you Leopold exponents. So this should be a quantitative because eventually you can follow that argument at least up to the point of the correspondence with exponents. So early times, so this is typically used in early time diagnostic of math before they get this time. And so this is not the out of time of the correlator. That's one thing that I just really wanted to point out. This is not the out of time of the correlator. This is the double commutator. But it's closely related to the out of time of the correlator. And how it's related is, well, let's just use a simple example where these guys are unitary. So let's choose W times W dagger equal to the identity. Also B and B dagger. Let's just expand out what we see inside this correlator. Or you would have the expectation value of W of T, B times B dagger, W of T dagger, minus B times W of T, B dagger, W T dagger. We'll get another term that's T, B, W of T dagger, B dagger. And the last term is B W T
double area, and because we've chosen them to be unitary, this piece over here is just going to give me W times W of T, or W T area, that's also the so let's say unity. And this combination here on the bottom right is also there. So it's just going to be unity. So in other words, if we normalize things correctly, these two factors are just going to give you 2. And these two ones are complex conjugates of one another. So I'm going to be 2 minus 2 times the 3 ones of expectation value of V, W of T, V value, W of T. This quantity here is called the overtime. And the way that it's the time of it, well, V is a value of T, okay? W of T is a T. So you don't have any time ordering at all between these. It's sort of mixed up. The ones at 0 and the ones at T. This one is called the time we talk about that. And certainly in this example where you've chosen unitary operator, you see that they are very closely related to one another. So this quantity over here is expected to increase exponentially due to the vehicle of exponents. This one over here should decrease as a function. So this should, this should be the case, so the combination is exponential. And often people just compute the overtime calculator because they should contain equivalent information. Now, other references, one that I want to work with in some detail is a computation of the non-point level, which should grow between according to the graph. And before I do that, well, I should just make a question.
Do we know that anyhow that OTOC term will not exceed 2? In that case, it becomes negative.
So if you've normalized things appropriately, then it should just work. But also, if you've started off with something that was a quantity times its complex conjugate. So this should always be a positive quantity. So that seems you're guaranteed that this should work. The factor of 2 here was just that, as I said, just the way of taking these notation values should be normalized. That's why I want it works. But yeah, in that case, from the starting point, that's why you're sure that this will never exceed 1. So this will grow to a maximum value. This will start at a maximum value of 1. So this should be correct. I think that's right. And it goes to 0. So
again, if you're in a non-chaotic system, then C of T should be bounded or should be just be 0 or should be what?
So in computation, we're going to do short ecosystem. I think this is true. What you start off with is what you compute the vehicle exponent to this. So the vehicle exponent, what you have, some of the C are e to the lambda r times t. So in the model that I'm going to introduce, it's going to be pretty clear that you should see vehicle exponents. And what you then want to compute is are all these vehicle exponents, are they positive vehicle exponents? If in an integrable system, you will be positive vehicle exponents. Or at least you won't get, even if the function is growing, it won't grow exponentially. So you won't be able to isolate the logarithm on this, you will be able to isolate time.
But the C of T is not whether it's constant, it's whether it's growing exponentially or maybe it's growing linearly or something. That's the solution.
That's the question. So if it's going exponentially, then it's a system. And the argument I've given so far is based on the semi-classical analogy. But there are arguments that this should extend to even, that this is not necessarily restricted to the semi-classical picture, but there are papers that picture that is actually quite important. So I'm not sure which one is the truth. The jury is still out on that. But the arguments not appealing to semi-classical pictures is essentially the following: that what you're computing here, so if you think of the computation being, you have some thermal state,
And what you're doing now in this combination in the time of the problem here. So I've chosen this, chosen to open this one, you could have chosen to write down this piece and it should be your occupation. For this argument, this is actually the most semantic piece, but since you're taking the bigger part, that's perfectly fine. So we've got V W, and then we've got E to the minus ITH W E to the ITH. And then the increase of the is V. So the argument goes that you have some thermal state, the increase of the is V. So the argument goes that you have some thermal state, and to that you now added some perturbation added by the V gain. V gain is acting on the beta state. Then what you're doing is you're evolving it time, and then another perturbation evolving back in time. So this is what it happens. And the question is, if I now act with the inverse of V, so in this case it's geometry, I act with V, so you're essentially asking, can I still see the presence of this perturbation that I made initially after this time evolution? And the claim is that in a chaotic system, that will not be possible. The information related to this perturbation that we added would have been mixed in with all the other information in the system, and we won't be able to cite it. And that's why it's over time all the correlator should decay into zero. As you increase the time, it's going to be more and more scrambled close to the system. So that's the argument based on multiple. That's the argument based on multiple in the classical picture, but based appealing to the formalization properties of the systems. Why this should work. All right. So having said that, let's start to because I think this point is appearing in a lot of literature. I think it's worthwhile to go through just an explicit computation of this in a practical model. So what I just want to do now is just sketch the outlines of this computation, taking note of some of the highlights of the lessons that we learned along the way. So the model, this comes from a very nice paper by Stanford, that is quantum chaos. But the reference is 12.687. And I think it is many body chaos of the company. It's the title of it. And the system that he's considering there is the following, where it's a matrix model with the following Lagrangian. The Lagrangian is given by R, plus the trace of the part, squared, minus L phi, squared, minus U squared, phi squared, and then with an additional order interaction, minus 2G squared. And of course, you've got a massive propagator, this bit, and this bit is going to be treated as 2. And minus 2G squared are 5. Okay, so the first let's consider here is tree. And tree level will learn an important lesson on the structure of these convolators. Just to solve for the geopolitical experiments in this system. I say explicitly, one will still need to do the final few steps numerically, but you can do all the setup towards getting the geopolitical experiment relatively, and then just get experiments immediately from there. And so the double commutator that we're going to be considering, actually, is C of t, and it's going to be what it also just does, just for parameters, cancel some divergences, but it doesn't change the vehicle exponents. So just to split, when you're taking that formal average, to split the matter of rho into two parts. So the quantity is considered as a choice, square root rho phi AB tx. This commutator with the field of the prime B prime, square root rho, and these phi A prime B prime, phi A and then it's forming an integral over these. So the example for standard big. So this is what we study. So just a tree. So no interaction is switched on. So you just have in mind the massive propagated force fields. And we're of course going to do weak contractions, complete reprogrammated. So tree we're going to have, I'm just going to sketch it schematically in a row. And then I'm going to get four possible terms from this. We had the complete and four different terms. And I'm actually just going to focus on two of them because that already illustrates the idea. So I'm just going to take some field phi, and I'm just going to take phi AB, phi A prime B prime. I'm just going to suppress the space and time formulas. Now, they'll do for time. Maybe they're different space and time formulas are important. So we need the combinatorics of the projections. Phi A B, phi A prime, and we've got phi A prime B prime, phi A B minus phi A B, phi so I've taken two of the terms in this contour in the context of space. And of course, you'll get a corresponding loop for the other two down here. I'm just going to focus on this first one for the purpose of the insertions. So what you can do with the insertions is include a 5 to the 4 interaction coming with the minus g squared. So that means that on this contour, I'm going to have to add 4 additional fields. And I can do that in several places. It turns out that the only two ones that are going to matter are going to be on this time here. So I can insert them either over here, top loop, or I can insert them on the bottom loop. So I'm just going to redraw these guys over here. And we can insert this as such.
Sorry, Yaku. I might be confused here, but the positive term in this commutator, isn't that one with the blue insertion first?
Oh, yes, you're right. My apologies. Yeah, so there's an overall minus sign in this. Yeah.
Right.
Actually, cool. Yeah, that's an overall minus sign. Yeah, absolutely. All right, so these are the insertions that you can make. And now it's important that this is due to the time arguments that you have. When you're inserting the fields here, you're propagating from 0 time, forward in time, and back. And same for this one over here. But over here, you're propagating down forwards in time in the blue insertion and propagating backwards in time. So in other words, that comes with an additional sign because you're not propagating from 0 to t, but from t to 0. There's an additional sign that comes in place. So that's the correct ordering for these insertions. So you've got a sign coming from a commutator, and you've got a sign coming from the fact that you're on this contour, and you can either be an insertion between 0 and t, or between t and 0. Oh, actually, okay. So now that we have that, so we now have to do the insertions now. This is just the first order. Now that we've made the insertion, I can again do the recontractions between these. And the connected recontractions are always going to be of the form where I take one of these guys contracted with one of these four, it's going to contract with this one, and one of these four is going to contract with this one. Similarly, one of these fields is going to contract with this one here, one of these fields is going to contract with that. So this is going to be important. And there are four different terms that you get in this case. So let's just write those out, what you get from this calculations. So from the quotations, I'm going to get, I'm going to have my phi and b, phi a prime b prime, and then for that, so that's for the, so that's for the, we actually write the first term. Do it. It's phi and b. I'm going to have phi and prime, and here I'll have my 4 phi fields that I'm doing. So that's something to read at time. Phi. I'm just going to split the two that I'm going to take off, and then we're going to get to phi squared after you come to the operations. Whereas that second one is going to have those fields here at the beginning. Phi squared on. And the bottom one, the bottom two, just keep track of the size. So this is from the top right, this one's from the top left. This one is going to be from phi a prime, then the phi and b, and then the 4 insertions. Phi squared prime. And then the bottom right is going to be a minus, first the phi b, then the 4 ones that you insert, phi squared is phi times the phi. And the contractions, as I said, is just here. There's going to be some combinatoric factor that's going to be associated with which field exactly you're doing the contraction with. But for the purposes of this combinatoric argument, it's not too important. I'm going to take this one there, that one, actually, this one. So you get these 4 different contributions. And what you can verify for yourself, exercise, is that what you end up with is again the structure that's reminiscent of a commutator. So what you're going to get is you're going to have phi AB, this recontraction, the reversal of that phi B. This recontraction multiplied with phi a prime and b prime, phi minus phi a prime. These recontractions multiplied with phi squared. So these go back to this phi squared that not yet being contracted. I'll explain why in a second. But this is the structure that you get. All the fields that I, in a sense, contract with that commutator structure will again give rise to a commutator structure. That's the combinatorics of the contractions. All right. But now, of course, all need to be contractions with that phi squared. And you can do it in 2 ways. You can either contract this this file itself, it's going to give you a correction to the self-energy. So, and that can be accounted for, that's nothing in the paper. But for our purposes, that's not the important point. The corrections to the self-energies do not give rise to the real exponents. The things that give rise to the real exponents are the following, so-called ladder diagrams. And they come about from where we had these, so this is the one picture where I wrote in the sort of time contour picture of these insertions. But what you can also do is visualize it in another way. So, is there a question? Sorry, just wondering how much time do you, closer to the end, how much time do I have left? 5 minutes. 5 minutes. I should be able to have 1 minute. All right. So this is the picture that we have over here. What you can visualize these as is two lines of a ladder. I've got my phi A field, phi AB field, and my phi A prime B prime here. This is the tree level that we have. When we insert these phi to the 4 fields, they're going to, you're going to insert them, and then two of them are, one of them is going to be contracted here, the other one on the opposite side. Right, so there's one contracted here, one contracted there, and then there's two that are aligned. And similarly on this side, two that are aligned. And you can contract them with themselves to give you a self-energy correction. More interesting thing you can do is to contract them opposite sides of the ladder. So this now gives you something that's like on the side, I get harder propagators. Along here, I get simple white propagators because they don't have a commutator sitting inside. The commutator is only along the rounds of these. This is now a single rung inserted on the ladder. This is for a single insertion. But of course, I can have two insertions. I can have a case where I have 5, these two fields. I have a single insertion on the ladder, these two free fields. Right. And I can contract it this way, two. Of course, you can
That's actual information.
that's all information. Exactly, that's all information squared. And this is the leading large information. The other way that you could have contracted it is, of course, to contract this one over here, over here. You can have sort of cross lines, but that's sub-leading here. There's now fewer free indices for that before expression. Pretty small arguments you can see in the Venn diagram. Right. Another point is that these ladder diagrams are the one that give rise to the Diagonal exponents. And I'm not going to run through all the details, but I'm just going to give the highlights of why that is the case. Why that is the case is that you can set up a recursive relation for this. So in other words, look, so the full diagram, so the fully reduced leading large in diagram, let's just call that this block over here. Insert it infinitely many rungs, I sum over all of those rungs. That is going to be the same as the empty diagram plus the full diagram with a single rung. This is the recursive relation that is going on in this. What this gives rise to, you can do for Fourier transform of these insertions. You get a very nice description in terms of the combination rules for these lines. But the point is that you set up a recursive relation. This recursive relation is to matrix relation. I'm just going to flash out for the details. I'll post these notes to the website as well if you want to have a look. The point is that this eventually gives you an expression as follows: an integral equation where this hopefully traced diagram you have. It's going to be given by, you're going to take the retardant propagators. Also Fourier transform time to omega, Fourier transform the x's to p's. But this is the quantity that you have, omega minus p. So this is for that empty diagrams, the two retardant propagators. And that's going to be multiplied by 1 plus integral of e for k 2 pi 4 there's going to be some combination of target propagators, white propagators, that's just called function in this case. This is how it gets upward, and all follows from this this conversion. Now, there's an argument for why you can drop this contribution, which I'm not going to, which again, I'm not going to go into details, but the point is that if I just stare at this piece of this, so just this f omega is equal to some function of p omega multiplied by this integral function times f of p. This is an integral equation, but it contains the same sort of idea as the derivative of function with respect to x is the function itself. Right? That's what this is doing. The f integrated with some other function multiplied by itself. I should get something exponential from this. The coefficients of that exponential are eigenvalues of this guy. So to get the Leopold of exponents in the problem, and also let me just make it very clear, this explains nicely why you see the exponential growth. It's due to this exponential proliferation of the ladder diagrams. That's where exponential growth comes from. And we see that this recursive equation that essentially implies that you'll get exponential as well. And the eigenvalues of R are the Leopold of exponents. So to get the leading Leopold of exponents, take that function, diagonalize it, pick up the largest eigenvalue, see that it's positive. It's positive, the exponential growth in the problem, and it's a chaotic system. Which I continue to do in the paper. It's a unitary kind of evolution. So they they're below the Stanford Schenkel on the same point. So the vertex is down. So everything is, it's a good check that things are working. That's how the computation goes. So just let's take a step back. The key things I just want to highlight is the fact that in order to do this computation, there's a lot of irrelevant things that we do. The important thing is the combinatorics of the weak contractions. That's the first thing. The second is this very special kind of contour which I'm including the insertions. The additional signs also helps with the combinatorics. And then the final flashpoint is this exponential proliferation of a particular class of diagrams, for which I can do diagonalization explicitly to get the idea of I think that's a sensible point to
Thanks a lot, Ken. And I'm sure there's questions, but they're also kind of waiting for us at the lunch place. So maybe if there's any urgent questions, otherwise we can discuss over lunch.
So I have a confusion that when we have the major chaotic where the kind of exponential divergence of classical prediction. But in quantum system, there is no longer prediction.
Yeah.
There should be some quantum generalization from the output.
Yeah, I think so. So certainly, so there is the formalization argument of why there should be a growing function at least, because you can argue for formalization that the function vanish. But I've not seen a good argument for why you should get exponential growth. Exponential growth is really the growth that's associated with the classical forms. You still have, in some coded systems, a semi-classical picture, but not in the so yeah, it's, I also had a leading point of view to a paper where they show that you do not see, it's in the Simon Bullions problem, where you do not see exponential growth of the OTOP, even though expected. The reason that they say is that we don't have a good semi-classical limit. So that is a bit concerning for me. With, if you don't have a semi-classical limit, whether you will see the vehicle.
If I can just comment on that, there was a paper by Hanada a few years ago that did look at quantum generalizations of ELL exponential by
Right. So we now better off the room. So
this run is coming from, so this is this curve. Right, so
Exactly, so what you can think about the direction.
so it's one of the various.
They'll be one of the lines, they'll be one of the flaws.
So my question is the second, like the other side of the axis. So is this all coming from the first computation? That's right. And this is the second computation. And then each of them is and you can have it.
Yeah, okay, then one thing that, one thing to check is that, then you pick up
This guy is something. Okay, so we made it.
Yeah.
But this is something that, again, I'll see you guys.
And you mentioned that the contractions from one side just give you a mass, like the mass confrontation.
Yeah, exactly, so they give you a version of something that you get. But it's not true in the so it's true in this one of Stanley. We obviously played the way there is similar computation on the fishing. In the fishing theory, you get symbols of contraction, symbols of structure. But in that case, the self-based correction is self-correction. So you can just talk. There's no self-based correction in that theory. But it's all done with specific fields and when you contract the indices. Something like that. In this model, there is correction, but in something like the fishnet model, there isn't.
Cool, and then one more thing. So this, I thought that was really cool, your argument about this being essentially a derivative.
Yeah.
And that you expect, you can see that you're going to get an exponential out just by the structure of this integral equation.
Exactly.
Which is pretty nice.
So this round function is really the key one. So-
And is this, am I being silly, was this basically kind of like the Schwinger-Dyson story that
Exactly.
that you get from this, right?
Exactly.
So if you write this guy as an integral equation, then you can already see,
Precisely.
because as you said, because of this proliferation, you can already see from the structure of this that you're going to get something that's exponential. Man, that's cool. I never thought about that. I think I just never got the fun paper, to be honest, to the point that I actually, but that's a really nice observation about. Yeah,
Yeah,
but
so
the
it's,
exponential.
Yeah, so it's quite early on that you're going to see Leopold. Which is quite nice.
Cool, because then I suppose it's another way of thinking about when you would when you have this kind of a structure to the Venn diagrams, you can already
Exactly.
you've seen chaos there already.
Exactly. So I think, so generically, you want to identify a family of diagrams that will correct exponentially. Those are the ones that give you the planetary exponential growth of the top.
No, that's,
Oh, that was of the double complement.
right. Oh, that's really cool, man. Thanks. Right. Perfect.
Yeah, and then lock this one.
Okay, let me try.
Yeah, this is lock. So, it is lock. I lock.
Oh, you want it?
So, you can go out through here. It only opens the front.
Maybe that's what you want me to do. Let me try that. Let me try that.
I think it's an explanation for that, right? So it's a rates due to the non-military evolution. So people they get these.
I have this non-military.
Exactly.
Yeah. But I was just wondering if you were doing it for, if you had that over terms.
Yes.
Before, you'd say more or less the same. Would this give you a different outcome in the planar limit, but then the one over n corrections, if you had these diagrams? It's not linear.
That's not my that's not
So maybe these would lead to this conversation, but not. Actually, no, I'm just wondering, no.
Yeah, so this one is, some people sort of indices that can speak over, but yeah, certainly so it's specific point limits. That's the thing.
Nice Christmas present.
What, that's not?
Nice Christmas present from Chris, I guess.
Yeah, it's a bit annoying that the middle is taken by the screen. But somehow also and you don't have a screen which goes. It's not. I think most of the people are working with the slides, so the kind of like, it's only the only person talking to read the use of that. In the meantime, I need my, I don't wipe it when I'm done. Yeah. And then. Yeah. It's all better, it's all better. You're kind of obliged to do all the steps. Like mistakes and the point out mistakes, like it's nice that, there's some interaction. For the slides, there's nothing to say. It's presented as if it's the truth. Yeah, the set is not. You can write and it's not just nice coffee, it's filter coffee. It's okay.
Yeah, and, but I have to think, right? I can try to do
Sure. Yeah. Start the camera. Is the vanaf ook gekort? Right, so welcome back. So for our second set of lectures today is going to be, we're going to have Sam van Doven, who's going to talk to us about supersymmetric indices. So we're looking forward to it.
Okay, thanks for having me. Good to see you all. So yeah, the title of these lectures will be supersymmetric indices. So let me briefly motivate the lectures and specifically supersymmetry. So yeah, maybe before I start, I should say, please interrupt me. I prepared somehow quite, I think, detailed lectures, but if it's very familiar or if it's boring, then you can speak me up, but we can also slow down. And we'll see where we get. But you can let me know. Anyway, so motivation. So, well, first of all, and probably many of you know that supersymmetry is a symmetry that exchanges bosons and fermions. That exchanges bosons and fermions. Right? And that's right. And that's already a little bit problematic phenomenologically because from a phenomenological perspective, we don't see a spin 1/2 photon or let's say a spin 0 electron. So if supersymmetry is a feature of our natural world, then certainly it's broken. And maybe it's not even there. And I guess sort of the recent experiments at the LHC are not particularly positive for supersymmetry, although, and especially for the phenomenological motivations for supersymmetry. But luckily, we have this, right? So we actually have a different motivation of studying supersymmetry, and I want to focus on that motivation. So as a happy age person, this doesn't affect us too much. And the essential reason is that supersymmetric observables, typically only get contributions from a limited amount of both perturbative and non-perturbative effects. I hope my country handwriting won't want me to do that. And in fact, so often the fact that it's only a little. Okay. Okay. Yeah, the fact that that's only a very limited amount of effects one has to deal with actually often makes these quantities exactly computed. And that's what we as theorists like, of course. In particular, why do we like that? Well, it allows us to study quantitatively various non-perturbative effects in quantum field theory. So you can think of sort of famously that won't be part of these lectures, but confinement in supersymmetric versions of QCD could be studied quantitatively, making use of supersymmetric techniques. Also, especially in string theory, but already within quantum field theory, we can study, we typically need these exact quantities to study things like dualities. Some dualities allow one, require one to have exact constants. And let's see, yeah, and an important duality in string theory is ADS-CFT. And it is actually in ADS-CFT that the supersymmetric indices, the compute. So our supersymmetric observable that we'll be interested in is called the supersymmetric index, the Witten index. And those have played in the past and also recently an important role in understanding black hole microstructure. Okay. So, yeah, so these are very, I'd say, very theoretical motivations for supersymmetry that are not so much connected, I guess, to experiments in LHC, but still, I think, are an important motivation to study supersymmetry. Yeah. So, okay. Yeah. Right. And then actually, okay, so let me now give an outline of the lectures. Any questions about motivation? Maybe I should. How did you do it, Jacob? Did you start on one side or alternate?
I started on one side and then propagate again. So it's But I think
I think it makes sense to alternate. Let me put it up. Outline of the lectures. So we'll start with supersymmetric quantum mechanics. I'm going to briefly abbreviate that with SQM. Actually, the main interest is really in supersymmetric QFTs. But as it turns out, many of the supersymmetric arguments, so the essence of the role that supersymmetry plays in the exactly computable quantities, that already appears in supersymmetric quantum mechanics. And we don't have to deal with all the bells and whistles of the Lorentz group and its representations and spinners and whatnot. So it's actually to focus on the supersymmetric, on the arguments from supersymmetry is actually very transparent and useful to look at supersymmetric quantum mechanics. And in particular, we'll start with the operator formalism, as is usually done in courses on quantum mechanics. And we will look at supersymmetric Hamiltonians. This supersymmetric algebra. And then we're ready to introduce our supersymmetric protocol, the Whitman index. Okay. Then the second part, which I'll probably turn to tomorrow, will be the path to the goal. Path to the goal. Formalism. And yeah, depending on what you guys feel is useful, we start off with some non-supersymmetric examples of how to compute the path integral. And we'll look, instead of a supersymmetric Hamiltonian, we'll look at a supersymmetric action. And then again, turn to the Whitman index. But now from the path integral perspective. And it might seem as if we're doing the job double, as if we're doing double the work. Why not stick to one issue? In terms of mathematics, and more specifically in the context of geometry. So it's, even though this is not, very directly connected to our main motivations, it's yeah. It turns out that the supersymmetric quantum mechanical framework gives a very nice perspective on some mathematical results that we're gonna at least mention, and depending on time, studying more in detail or not, we're going to introduce the supersymmetric sigma model, and then discuss how the Chern, Gauss, Bonnet theory. So remember that the most basic version of that is that the integral of the Ricci tensor over a Riemann surface of any metric gives this integer 2G minus 2 or 2 minus 2G, I'm not entirely sure, but anyway. So that's the basic version, and this is a more general theorem. We're going to see how this theorem emerges naturally by combining these two perspectives on specific context. Okay, and then if there's time, so I can't make promises, but if there is time, we'll discuss briefly how these ideas extend to supersymmetric quantum field theories, particularly in 4 dimensions. And I would be really happy if I can just introduce the superconformal index. Which is a version of the Whitman index in these higher dimensional field theories. So, yeah, but I think as I said, many of the arguments that we'll see here, they'll just add some bells and whistles, but essentially the same arguments go through in any point. So that's the outline. Any question about that? And then we'll start. Okay, so operative formalism. Okay, so I'm gonna start, I guess, a little bit low broad. I'm not gonna start with specific algebra, but first gonna focus on 2 fairly ordinary, maybe fairly general, also Hamiltonian. There are 2 Hamiltonians. One H, written as here. And another Hamiltonian, H tilde, is A dagger. Okay, and here A dagger, so generalized versions of the ladder operators to the harmonic oscillator. There's an IP part. And then, right, a general function, or the derivative of a general middle function h of x. And a dagger is just the Hermitian conjugate of this, right? So it's the square root of 2 minus p plus x. Okay. So as usual, we have the commutation relations x t equal to I. And if you take, if you would take h prime of x equal to x, or the function h of x equal to a half x squared, you get the ordinary harmonic oscillator. But these guys are clearly more general because we allow it to be a general real function. Okay? Okay. And the goal is to show that these 2 Hamiltonians, the spectra, combined spectra form a supersymmetric system. So that's the goal. So let's see how that's going to work out. So we can, first of all, we can just compute them slightly more explicitly. Usual, just work out these products, taking into account the operator nature of the P and X symbol, and then you get the half P squared plus a half H prime X squared. X squared. Let's see. Get minus a half H double prime of X. Yeah. And H tilde. So this H double prime comes from an action of P on H prime, right? Because there's this product with a double prime. H tilde is exactly the same, but it has a different sign. It's plus. Okay? Okay, so let's look at the spectrum of these guys. Properties of the spectrum. Okay, first property is that the spectrum is positive. Meaning that any energy eigenstate has an eigenvalue, it has to be larger or equal to 0. So how to see this? Well, let's look at an energy eigenstate of H. This is true, this is true for both Hamiltonians. Let's look first at Hamiltonian 1. That's psi m denotes an energy eigenstate, energy eigenvalue En. Then we could just compute. This is how to define the eigenstate. But just if we want to compute the energy, we write the inner product psi m with H, and H is A dagger A. A dagger A. But this now I can write as the norm of psi m, because there's a dagger here. And the norm is always larger or equal to 10. Okay, and the argument works exactly in the same way. Well, works the same for H. Okay. Now, more importantly, there's a pairing between the spectra, H and H tilde. Okay, how do we see that? Well, I'm going to claim that if I have an eigenstate of H, this psi m, I can construct an eigenstate of H tilde by looking at the following scene. So I define this guy to be A. I'm not going to worry about the normalization by the way of these things. I'm going to write A psi m. Now, is this how to check that this is an eigenstate of H tilde? Well, just act with H tilde. So that is a dagger A on psi of m. But now you recognize the untilted Hamiltonian here. That gives eigenvalue En, and then I act again with A, which gives me back psi tilde. So this is indeed an eigenstate of H. Sorry, is it still readable? I hope it's readable. Right, so that's clear. Okay, so this means that for every eigenstate psi of H, we can construct an eigenstate of H tilde. The opposite is also true. So for every state psi tilde, so for every state of psi tilde, I can also construct the state of psi n. By acting with AN. Okay. So this, so there's a bijection between the two spectra for general energy eigenstates, except for one state. So this argument fails for state with E equal to 0. So, fails for E is 0 states, which are necessarily ground states because the minimum energy is 0. So why does it fail for these states? Well, as we said, the energy eigenvalue E0 is equal to the norm of the state. And so let's say that we have this ground state, psi 0, 0. And this state, we try to construct the eigenstate of the tilde Hamiltonian. We write A acting on psi 0. But this is 0 because we already showed that E0 would be the norm of the associated state. And if it's 0, then the state is actually equal to 0. And this is the another state. So A annihilates the ground state. Okay? And this is also true. This is also true for the tilde component. So if there were the state psi tilde 0 with energy 0, then a dagger acting on this state, which for the finite energy states would provide us with this partner state. In this case, annihilates psi 0 tilde and does no harm. So, in other words, all finite energy states are pairs between these Hamiltonians, but ground state is not necessary. Ground states are not. No. Okay, now for the class of Hamiltonians that I've introduced, the statement is a little bit stronger. So it turns out that there are three possible spectra. So either there is a zero energy ground state for the tilde Hamiltonian, or there is a zero energy state for the untilted Hamiltonian, but they can't both exist, as I will show now. Or there simply doesn't exist a zero eigenstate. So let's see how that comes about. So if we look at the wave function, of these zero energy states, we have the following property that psi 0 is a zero eigenstate of the Hamiltonian, then this will be 0. And this implies the following equation for the ground state wave function. It tells us that ddx plus the h prime of x acting on psi 0 of x is equal to 0, right? I'm just plugging in the operator. But this is a very simple differential equation we can solve exactly. It follows that we can express the ground state wave function of a zero energy state. We can express it in terms of this function h. With some normalization times e to the power minus h of x, which you can easily check to satisfy that equation. Okay. We could do the same. This is for the h zero eigenstate. We do the same for, again, we do the same for the h tilde energy eigenstate. Similarly, implies the differential equation that gives for this wave function subject for normalization factor e to the plus h of x. Okay. That's just because of the sign difference between this a and the b. Okay, but now we see that these ground state wave functions are well behaved. Well, the first one is well behaved. Let's call this one. One is well behaved. Only for a specific function h of x. And for a subclass of functions h of x, namely, if h of x goes to infinity for x to infinity, then only then is this guy normalizable. And similarly, 2 is well behaved for h of x to minus infinity for x to infinity. Okay? But here. Okay. So that means that so this in particular means that if h of x satisfies this requirement, then this psi tilde of 0 is not well behaved and therefore doesn't exist. It's not in the spectrum, and vice versa. On the other hand, if h of x doesn't satisfy either constraint, which obviously can happen, then there will not be a zero energy ground state at all. Meaning that in that case, all states in the Hamiltonian are paired. Because remember, all the non-zero energy eigenstates of these Hamiltonians are paired. So let me draw the spectra to make that a bit more clear. We have these three possibilities. So this is for h of x going to infinity asymptotically. Okay. We have eigenstates of our h, eigenstates h tilde. Now, when this is obeyed asymptotically, then there will be a well-behaved zero energy eigenstate of h, okay. And then various other states. All the other eigenstates are pairs. H tilde doesn't have this zero energy density, right? Okay. We can draw the same picture for the case when H goes to minus infinity asymptotically, the spectrum will be of this form. And finally, if here, if H doesn't have either property in the spectrum, like this. Okay. Okay. Okay, so any questions about it?
In the otherwise case, is the fading like same state to same state?
So
In the otherwise case, how's the fading?
the pairing is exact. So the energy eigenstate.
No, I mean, is it like this one to this one and this one to this one, right? Corresponding one.
Yeah.
And do we have fadings in
Sorry,
the
I forgot to draw, but so we have seen that A dagger, sorry, A brings us from an eigenstate of H to an eigenstate of H tilde with the same eigenvalue, and A dagger takes us in the other direction.
and the fading in the other two?
So here the pairing is the same with A and A dagger, except for this guy, because this guy is annihilated by A. There's no corresponding state on this side. And it better be, because we know that the ground state wave function of an E is zero state for this function, which is not lovely. So for the same class of Hamiltonians, it's actually, if there is a zero energy eigenstate, it can only be of H or only of H tilde, but it can't be some. There are more general quantum mechanical systems that we'll also see later in the lectures, where it is possible that there are both, okay, so I'm going to use the words bosonic and fermionic ground states, because that you'll ultimately see that that's the difference between the two. But they will never be related to each other. So there can be some of these guys, some of these guys, but they don't map to each other.
Can you explain about the generics? Can these laws be the generic?
I mean, I guess for sufficiently generic functions, H not, right? But probably, yeah, for special cases, I guess they can be generics. Yeah.
But even then, each one on that side will have the corresponding. So if there's three that correspond to one red dot,
Yes.
still be three corresponding to the three.
Which is ultimately not that surprising because these Hamiltonians are homogeneous. Right? They have the same potential. I just erased it, of course, but there's only that sign difference for the last. But that property is completely.
So just a simple question. Generic rules of H can the spectrum be both discrete and continuous, or you just do not continuous spectrum?
So, I mean, I guess I think I'm assuming generically a discrete spectrum. These are positive definite potentials that have some polynomial shape generically. But yeah, there are models with continuous spectra. I'm not entirely sure.
Yeah, I suppose if you have some finite height somewhere.
Yeah.
The combination of discrete and continuous.
Yeah.
I think like it is a supersymmetric pair of one-dimensional potential then, and for getting the name of the other potential, and the one-dimensional potential I think will have discrete as well as continuous one. So
Okay.
we need answer.
Okay. Yeah. So that has supersymmetry. Okay.
Question level.
So quotient element.
quotient element and one
Is
dimensional.
that the cosine, guys, the cosine element one?
I don't know.
Yeah.
Or we can look it up. Yeah. I think generically for polynomial h, there won't be.
You have a charge that needs to have that. Right?
Yeah. Yeah. Yeah, so we'll get there. I guess so. Yeah. If you can find a function h of x that has a continuous part of the spectrum, and you follow this construction through, you're guaranteed to have this part zero. Okay, so of course this reeks like symmetry. So but how to formalize that a bit more concretely? So that's the next part of this hour, which is the supersymmetry algebra. Okay, so far we've looked at fairly, in some sense special, but also fairly generic Hamiltonians that don't obviously have anything to do with both, well, not obviously anything to do with Fermions. Those are variable x. So how do fermions come into the game? So let us introduce some two fermionic operators, psi and psi there, that satisfy the usual fermionic commutation, anti-commutation conditions. Okay. Well, just to remind you, you can think of two operators satisfying these anti-commutation relations as fermionic ladder operators. So let us introduce the fermionic number. Fermionic number operator. And you can check, it's a good exercise, perhaps, or maybe easy. This are ladder operator. These commutation relations are satisfied, which means that they behave as ladder operators. Okay, so then we can define, as we usually do, the ground state, 0, such that the lowering operator annihilates this vacuum. And then there's only one other state, because of the Grassmann-like nature. And then we have the creation operator and the vacuum, and that's these two states form a two-dimensional representation of this integral. Right? We can't add anything more because psi squared is equal to 0. Okay, so these two guys have fermion number 0 and 1. Okay. Okay, so now I'm going to write down the supersymmetric Hamiltonian. So we're going to use these fermionic operators to combine H and H tilde into a single Hamiltonian that takes the following form. I'm just going to make a very specific association. It's essentially the same initial part. But now, in the last term, where in the previous time we had a different sign for either one, we write down the single root. Plus the remains. Plus. And right? Because if we look at this Hamiltonian and we let it act on the zero state, we'll annihilate with the first part, psi dagger psi, right? But we'll get a 1 from psi dagger, we get a minus sign in front. But if we let it act on this second state, we get a plus, right? So this Hamiltonian combines the previous two into a single Hamiltonian. Okay, and the eigenstates will just be the same that we already saw. So the Hilbert space of the theory decomposes to a bosonic and a Fermionic parts, where the bosonic parts are just these square integrable functions. And combined with this first bosonic vacuum, the fermionic state Hilbert space is the same. But now combined with the fermionic vacuum. Okay. Okay, and well, we've already seen how to map between eigenstates of the Hamiltonians. Now we can formalize that as well. We can introduce what are known as supercharges. Supercharges. I'm going to put charge between quotation marks because we haven't really seen that this is a symmetry in the sense of Noether, that there's some conserved currents. We'll get there, but for now, put that between quotation marks. The typical notation used for these charges is Q. Right. In this way, which is nothing, of course, but our operator A that maps us from H to H tilde eigenstates, but we just combine it with this psi dagger, right? This psi dagger just extends over so that we're taking it to the other side. And Q dagger is instead psi minus which is nothing but a dagger. So what we've already shown in the context of A and A dagger, but which you can try to check yourself as well, is that when we view X and P as operators, as we should, and similarly psi dagger, satisfying the anti-commutation relations that were on the board, we can check that the Hamiltonian commutes with both. Charges, which is
Isn't there a function for the del squared in the text? In the second line, after it equals.
yes, a function. Yeah, so, this guy this will contain all the wave functions associated to, all the wave functions associated to the Hamiltonian, the eigenfunctions of the Hamiltonian will live in this space. Right, but we add sort of a label to it, which keeps track of whether we're sitting in the bosonic factor or in the fermion factor. Right, so we could also put a label, I guess, on this wave function that takes a 0 or 1 value, which corresponds to the fermion number. I use the convention to put a cat there. I hope it's not confusing. So this would be your, this guy contains the wave functions in the position basis. And then we multiply it by this two-dimensional representation. Is that
Shouldn't the adjoint of Q be A dagger side rather than psi A dagger?
you're saying this is the right dagger present with the dagger?
A dagger.
You're saying this is the right dagger present with the dagger?
I mean, like Q is equal to psi dagger A, right?
So once
So Q equals psi adjoint A.
side dagger, okay.
Yeah.
Yeah.
So if I do a dagger on that, take an adjoint of that.
Yes, that's right. But these guys can use. Is that the issue?
Yeah, these guys different spaces.
They're working different.
So I can actually define it there.
So they're good. That is an important remark, actually. This is the same. These don't see it. Particularly, there's no X dependency psi, this is bosonic, we don't have, there's nothing. But it is an important point indeed that Q is a bit silly to say that. The dagger Q is this Q. Okay. Yeah, so these commutation relations, they tell us that that Q maps all the states in the bosonic Hilbert space. Let's look at the subspace of energy eigenstates that that's number n to the fermions. At the same energy eigen. And Q dagger does the opposite. So they preserve energy eigenstates. Right. Okay. Now, another good maybe. So during the lectures, I'll put out some exercises now and then. And maybe a good exercise to check is that, again, using the commutation relations that were on the board, that the anti-commutator of Q and Q dagger precisely gives the Hamiltonian. Okay? And moreover, but that's easy to see, that Q and Q, anti-commutator Q and Q dagger are both equal. That follows just because psi squared and psi dagger squared is 0. But this one is perhaps a good exercise to check. Okay, and from this combination relation, we find that I'm not opening it here.
Just one more
It's
place.
not confusing.
We have not said anything about edge in that statement, right?
I've not said about
About edge of X in that bottom right-hand statement where Q and Q dagger are transforming to inventing.
So you mean the three different spectra that I have here? No, I haven't mentioned that yet. But the same applies. The same applies. But let me I think probably we get into what you want to ask me. So, yeah, give me 2 minutes and then see if the question is still there. So this last commutator tells us that if there is a state psi somewhere in the Hilbert space, whether it's in the bosonic or fermionic part, such that the full Hamiltonian H Susan acting on this state is zero, then this state is unpaired. The reason is again that if we try to act with Q on this state psi, if it were in the boson part, or if we would act with Q dagger, if it were in the fermion part, and this is right. This is not confusing, but I can write this as so. Again, we're going to use that is given by the norm of this state, exactly because the Hamiltonian is the anti-commutator of Q and Q dash. Right? Is that clear? And this is zero. If there is a zero in the eigenstate, that means necessarily that this state is an eigen. And we have the same arguments for Q vector.
So what we are saying is we have when we have to bosonic and fermionic Hamiltonians, we have the ground state. But when we construct the supersymmetric Hamiltonian out of it, we discard the ground state.
But we're not discarding. So we're not discarding the ground states. The statement is just that in the spectrum of the supersymmetric Hamiltonian, the ground state is never paired with another state. If there's a zero energy ground state, that doesn't spoil the supersymmetry. It might seem sometimes it's slightly confusing way of talking, because it might seem that here the symmetry would be broken. But actually, the way of saying this is that these Hamiltonians have a supersymmetry preserved in the ground state. Why is that? Exactly for these reasons. So if we have a zero energy eigenstate acting with the symmetry generator on the state, annihilates the state. That means that the symmetry is preserved. If this were non-zero, so if we're in the context of the Hamiltonian where all states are paired, then the ground state is not preserved by the symmetry generator, which means that the symmetry is spontaneously broken. So actually, yeah, I was about to get there, but actually we would say that this spectrum is a spectrum of a spontaneously broken. Spontaneously broken system. And if there is a zero energy eigenstate, the spectrum preserves. That's
What's spontaneously broken?
sorry.
What's spontaneously broken?
Well, because
This is the fight from the.
but but the ground state in this case is obviously this some finite energy state, the lowest energy eigenstate. And that one is not preserved by the supercharge. Right? So that's typically what we call spontaneously broken symmetry.
But it hasn't explicitly not.
Because the Hamiltonian is still written as supersymmetry, right? So the theory, I mean, I guess I'm jumping ahead a little bit because in the action formalism, we really show that this is a symmetry. This charge is the associated charge for that symmetry. And so the theory has the symmetry, but the ground state doesn't preserve its symmetry. So there are no offending terms in the Hamiltonian or in the ground channel, or whatever you call it. But the ground state doesn't preserve it. Okay, I think that's maybe so. One perhaps funny consequence of this. Perhaps I was a bit quick here, so let me just add the quick reason. So E is equal to psi to psi. But when H is written in this way, it's going to be written as psi H dagger plus dagger Q psi dagger plus dagger Q psi and a half word. And this is a term of this is a sum. This is a sum of these two. Norms. Both the more normal for both Q dagger side and Q side. And if that is zero, then both have to separately be equal to zero because it's the sum of the squares. So both annihilate this zero energy ground state, and then is when we say that SUSY is preserved. And then I should also say, so, it's believed that in our universe we have a positive vacuum energy, and that's in the Sitter universe. And so that's one way to see that the supersymmetry should at least be broken, at least be spontaneously broken in our universe, because positive vacuum energy is larger than zero. So if there is supersymmetry in our universe, we definitely don't have a supersymmetric ground state. A state that preserves, that is annihilated by both Q and Q. But we're in this situation, which we're obviously not, because we don't see that there, so there's a further gradient, but at least we are in this situation. Which we're obviously not, because we don't see that there, so there's a further gradient, but at least we are in a spontaneously broken situation with a positive vacuum.
So it's continuous breaking tend also to the excited state, right? It's not, I know it's still about the vacuum, but
Yeah.
you
No.
don't have
But this
sparks the same mass as sparks, in other words.
Yeah, for us, it should, for the real world.
For the real world.
For the real world, there should be further.
For in presence of gravity, the specific argument changes in time because if you have an antidiscipline space, there can be some
Yeah. How does that work? Oh, but that's because there's an S5, right? And some fluxes.
No, it's not the AES.
No. Can't
Yes, it's supersymmetry.
Yes,
There is a change in the reality by negative sign contribution. So
I see.
somehow we can the scalar potential is not possible in that case.
Oh.
We have a contribution from the negative.
stress that this holds in field theory, generally in field, but not in the. So yeah, what I was saying about the positive effective energies of so lacks all rigor, but it's just a funny observation that you can make. Okay, so let me stop there for now, and I guess we'll continue in half an hour.
In half an hour. So, should we work off the stuff? So. Oh, before.
Yeah. So we both have to be positive. If the sum has to be zero, both have to be positive.
And why do you want to
Oh, because
zero,
by assumption. So we're assuming that this is a zero energy state.
Okay.
And if there is a zero energy state, it's necessarily an identified Q. Now, it doesn't have to be a zero energy eigenstate, and then this argument doesn't hold. And that's why these states are partnered. Zero energy eigenstate, and then this argument doesn't hold. And that's why these states are partnered. So that's why the ground, so this is a ground state, right? Because it's the state, but indeed it's not annihilated by Q. There's a function.
Okay, so it must be like this was not the about two cases and we will not get zero.
Yeah, we get some finite number. It just means that this is not annihilated by the supercharges. And that means, but we know that is correct because we know that it shouldn't, because there is a partial state to which it's.
Oh, okay, that is because like in a supersymmetry element we have two parts. Right? So if it was one of the above two, then one of the terms would drop out and the other would give us some finite value. But since it's the otherwise case, both terms are not there and it and more. So and is the Simon asked the question before he was in the function, right? I think they had Simon asked the question before he was in the function, right? I think they had there is ideal here but not here.
Yeah, but that's because this is the this will be identified in both.
Oh, okay, so the basis here is all Bosonian.
Yeah, so this zero guy is boson.
And here also it's Bosonian.
This also does not
And but this takes
it's
into
the
the
same. It's the same.
or we could do it the other way. We could remove the side again here and side here and then the zero is from
Yeah, but the only thing is that we define. Yeah, you could do that, but then you have to define.
modify things.
Yeah, because we define zero to be annihilated.
Yeah.
By psi.
Yeah.
But we could also say that zero be annihilated by psi dagger.
Yeah.
And then the psi dagger will disappear there, and then you put a psi here. That's just a convention. You a student here?
No, I'm at UC.
Oh, you're at UC?
I'm actually with Yaku's same group. I'm working with.
I see.
I just want to list why it said that she broke it for knockdown state.
Yeah. So usually when properly explain that these guys generate a symmetry. We'll get there. But you can think of these as charges associated to a general symmetry through the notice procedure, right? And when you say that the state preserves a symmetry, when you say in quantum theory, you say that when you act with a symmetry generated in the state doesn't change. It's not changed. And the statement would be the infinitesimal statement of that
Okay.
So the statement here is that because in these two spectra, we have zero energy eigenstates. And we argue there that a zero energy eigenstate is annihilated by these charges. It implies that these states preserve the symmetry. Okay. Whereas here, you might think this looks like a more symmetric spectrum.
Yeah.
But in fact,
Yeah,
it's the one where it's spontaneous.
because these are generated, not the actual transformations.
That's it.
Okay, I see. That makes
Yeah,
sense.
now it makes sense.
Yeah,
Okay,
okay,
so-
that's generated rather.
Sorry.
Thank you.
Okay.
Can you just continue at this place? I can wait for 1 second and this.
Okay, that's good. Okay, thanks for letting me know that it's the right.
Well, at
place.
least for
That's
me,
also
like-
important. Here, sometimes we don't feedback and it's not clear, but this place is good.
Yeah. For me at least, I don't know.
No, yeah, okay. For you?
Yeah, no, this is good.
Yeah, okay, cool. Thanks.
Yeah. So.
Did it work? I guess it did not. This is having, that should be perfect. Okay. So I just want to, we had this general story for generic functions, h of x, for each of which you get some supersymmetric system, and depending on the asymptotic behavior of this h, you either have a supersymmetric ground state, meaning a state that is both annihilated by Q and Q dagger, which can be either bosonic or fermionic, but they can't simultaneously they can't be both bosonic and fermionic ground state for this set of entities. Or there's no supersymmetric ground state. All the states in the spectrum are paired, and supersymmetry is spontaneously broken. So that is a completely generic story. But let's look at some examples of this function h to see how this works. So let's start with taking the function h of x equal to a half omega x squared. So this will be, I'm going to write it just. So let's first notice that if omega, if we take omega larger than 0, then the asymptotic behavior disguise that h of x goes to infinity for x to infinity. If omega is less than 0, we have that h of x goes to minus infinity, asymptotic. So that means that in this case, we are satisfying the properties that are necessary for the existence of a supersymmetric ground state, which is going to be bosonic in the case that omega is larger than 0 and fermionic if it's less. Okay, so what is the Hamiltonian associated to this function? It's nothing but the harmonic oscillator. But with an additional term. So remember that I have to take, in the Hamiltonian, I have the derivative of this guy squared. Take a derivative and then square it again. That gives me a half omega squared, x squared. Right? And then, so that's this just the harmonic oscillator. And then we have an additional term where we have the second derivative of this guy, which is a half. What's a half? That's the second derivative. The second derivative is just omega. And then we have our fermionic part. So this is essentially just the harmonic oscillator, but there will be a shift in the ground state energy depending on whether whether on the bosonic or fermionic ground state. So this would be the bosonic shift. This would be the fermionic shift. Okay. So we know that we can write this, of course, as A bigger A. A bigger are just the usual ladder operators. Plus our omega. Right? So this is the ground state energy of the harmonic oscillator. But now we have this additional shift. I'm going to write it again. It's just the same.
Sorry.
Yeah.
We have HFX theory.
Yes. So I'm taking a derivative. So the Hamiltonian, remember that the Hamiltonian was defined as half e squared plus the half h. Hamiltonian, remember that the Hamiltonian was defined as half e squared plus the half h prime.
Yeah.
Does that make sense? Okay. So these are the usual letter operations. H coming together. H is minus A. H. You can build the usual spectrum of the harmonic oscillator, and in particular. If omega is larger than 0, we look at the ground, the usual ground state, so psi 0, the harmonic oscillator, such that A acting on psi 0 is equal to 0. This is the associated wave function. Is, as usual, equal to E minus 1/2 omega x squared. And that is indeed what we are talking about. Okay. Now, if we act with the Hamiltonian on this state, so it's psi 0, and we look at the vacuum, the fermionic space, and we get the usual ground state energy for the psi 0 part associated with this part, but now we get a shift. From this term, which is minus 1/2 omega, we get that this is a state of 0. And similarly, you can act on psi 0 times psi dagger. Now we get a positive shift. We get that this is equal to omega. Right? Well, the rest of the spectrum can be built up as usual, so we can act with ladder operators resonant without n underground state. And similarly, you can define the states times tilde times sorry, 0. Okay? So that's the spectrum, and the energy eigenvalues associated with these states are now the eigenstate on the boson reflection as energy n times omega, where n is equal to 0, 1, 2, etc. And the states until the omega, but now until the starts at 1. 1, 2. Right. And so here we see that for that the states E. So if I write this in this way, you see that on the bosonic side we have 0. The bosonic side, and we have a 0 energy eigenstate. And otherwise, the states are spaced in the so. Whereas on the fermionic side, we only start at n till the equal to 1 at energy omega, and then we go up. So this in this example, we see that if we combine two harmonic oscillators and shifting their shifting one of the spectra by minus a half omega and one of the spectra by plus a half omega, that defines the supersymmetric system with a supersymmetry with a bosonic supersymmetry preserved in ground state. Instead, if we would have taken omega smaller than 0, then the behavior of h of x is equal to omega x squared, is that it goes h of x goes to minus infinity asymptotically. Right? And in this case, the state with lowest energy is the fermionic system. So the state times 0 times sorry, dagger of 0 now has energy a half omega. Absolute value minus half omega In this case, this is. So I've just taken out the minus sign of omega and replaced it with absolute signs, and then you see that these guys change signs, so they stay with side everything zero. Okay. So in this case, so for omega less than zero, we have two harmonic oscillators, but in this case, with a fermion ground state, which reserves some state. Okay, so that's the example of harmonic oscillator. And you can also look at more general potentials. Still make some non-trivial statements. So of course we can't solve those guys exactly anymore, but let's see what we can say. So if h of x is instead a cubic polynomial, well then the first thing we can observe is that h of x does not have the behavior, either of the behavior of that's required for a bosonic vanishing energy eigenstate. Also not for a fermion quantum, right? Because this doesn't go to infinity for x. It's not true. It's infinity, but also not minus infinity, right? But it does both. So the ground state wave functions associated with zero energy eigenstate are both not well behaved. And so we already know that any supersymmetric quantum mechanics with a Hamiltonian whose h is given by a cubic polynomial has a spontaneously broken symmetry. In particular, the ground state of this system will be told that it is not being degenerate. Because it has to have finite energy, and that means it has to be it is paired with it. Yeah. We can say a little bit more because we can. Let's see. Because if we write, we know that the potential term h prime half h prime squared. Right? In this case, will be some quartic potential. So typically, we'll look something like this. And we also, it's not difficult to check that h, the second derivative of h at this minimum will be less than zero, and h double prime x here will be larger than zero. This means that on this side, this term will be negative, and that means that the energy can be lowered if this term is non-zero, which means that around this minimum we will have a fermion ground state associated with this, the non-vanishing of this term, whereas in this minimum there will be a boson. Now, in normal quantum mechanical systems, there will be tunneling, and the real ground state will be some linear combination of the semi-classical ground state associated with these two minima. But in this supersymmetric system, we actually really have two ground states. One that is centered here, and that is fermion. One that is centered here, that is boson. And they can't tunnel because they live in different parts of the room space. So there's no superposition. Okay. So even though we can't exactly solve the spectrum here. We can say quite a few qualitative things just based on the fact that the Hamiltonian has some symmetry. Okay, then,
So it's Masano because they have different charges. So you cannot superpose things that have different charges on their energy.
exactly. So the fermions, right, they should also return to themselves under exchange have a minus sign, for example. The boson should not have a property. So a superposition of those two states, we do not have a definite statistics in this graph. Okay. So, any other questions? So let me then continue with the written introduction to written groups. We're gonna define operator. We already have seen the fermion number operator, which takes the value 0 or 1, depending on whether we're in the bosonic or the fermionic ground states. So it was F, between side over side. Now we consider minus 1 to the power of F. Okay. This operator will be plus or minus 1, depending on whether we sit in H bosonic group, H fermionic. We're going to define the Witten index very similarly to the thermal partition function. So index I is defined to be the trace of the full Hilbert space of the field. And just as in the thermal partition function, we write down e to the minus beta h, where beta is the inverse temperature. But now we plug in an additional minus 1 to the F. Meaning that when we do the trace, and we're looking at fermionic states, they get an additional minus sign, apart from being weighed by their energy. Okay. So you might wonder why you would consider an object like this. And for generic theories, it's not anything special. But for supersymmetric theories, it turns out to be a very different object than the thermal partition function. And that's what we're going to do. So let me try to explain why this is an interesting object for supersymmetric theory. Okay. So to see why it is something special, we first recall that for supersymmetric systems, where we're looking at states with energy eigenvalue larger than 0, there's a bijection between the fermionic and bosonic. Over space. So we have this operator Q that takes any energy eigenstate in HB for HF and vice versa. So let's evaluate this trace on this larger than 0 energy eigenstates. So we get trace over H larger than 0 minus 1 to the F against H. This just becomes sum over all these energies. Sum over all these energy states N, where we have boson states here, minus with H. So this is just plugging in the definition of the trace as a sum over a complete basis of states. And now, on the fermionic part of the Hilbert space, we get an additional minus sign because we're measuring the fermion number with minus 1 to the f. But otherwise, you get the same, you get the partner states. Which in particular have the same energy eigenvalue, right? So the Q and P dagger commute with H. So this just evaluates to 0. They just cancel out precisely, right? So what remains is that the index of the full theory only gets contributions from the zero energy states. Okay. So in general, this would, since H is equal to 0, the beta becomes disappears. And we would just get the number of bosonic states minus the number of fermionic ground states. Right. That's in general the case. For the specific theories that we've considered so far, we've seen that either we have a bosonic or we have a fermionic ground state. So for us, this would either be plus or minus 1, or 0 if there are no zero energy states. Right? Is that clear? Okay, so we'll see more general examples. This can be any integer, positive or negative. But for the special examples we consider, this can only take these 3 values.
So it only counts the ground state.
It only counts the ground state. So in fact, even a little bit more precisely, it only counts 0 energy ground states. So it counts the ground states that are annihilated by this Q and Q vector, supersymmetry ground states. If there is not a supersymmetry ground state, so if we're in a scenario where the ground state has a positive energy, it will be partnered with another state, and then it would evaluate to 0.
So even if we are getting late information, very normally calculate partial function over all of it.
Say it again.
Very normally calculate partial function.
Yes.
So we cover all of it.
Yes.
So now what we end up here is ground state.
That's correct. That's correct. So yeah. So what this argument shows is that all finite energy states cancel out. So they appear the computation principle, but the contributions cancel out. And what remains is these unpartnered states.
But if you still have some information coming to then
so these are theories of interactions, right? So h of x is a general function. So yeah, in general there are interactions, and there's some non-trivial potential. But we only look at the ground states. In the Witten index, effectively only the supersymmetric ground states contribute non-trivial. Everything else cancels. All states that are partners cancel. Only equal to 0 states.
Sorry, it's a general question, but can we come up with a supersymmetric partner for any bosonic or fermionic and union?
No. So the potential has to have this somewhat so far we've looked at this. No, I don't suggest this. So far, we looked at this. I mean, there are more general Hamiltonians, but so there is this additional requirement that the Hamiltonian can be written as this. Sorry, say, we were looking at these H and H children that are of this specific form, right? So I guess, at least for this subcase of examples, you can construct a partner Hamiltonian if the original Hamiltonian already takes on the form effective from That's not completely changed.
So again, another question. So if we have like a Hamiltonian, that's an element of tensor sum of two algebras, 2D algebras. For example, let's say SU2, and then tensor product with tensor sum with SU1. So can I write such an Hamiltonian in this form?
If you could, then you're present, but I'm not very sure. I don't think this is general. You could write a Hamiltonian, a general Hamiltonian in this way. I'm not very sure. We'd have to think. If it's possible, then yes, we can start the partner Hamiltonian in this way. But I would say that this is at least the initial requirement. This is a sufficient requirement, but not a very short distance. Okay. Okay, so that is the rhythm index. So maybe it sounds a little bit trivial, but especially for our case, it just values plus minus 1 and 0. Maybe it's not that interesting, but it has a number of very special properties that make it interesting. And so let me explain those. Let me try to motivate why it is an interesting object. Say that again. Yeah, this thing will have a geometric significance. Yes. We'll see that later. Yeah. Okay, so the first observation that I already made is that I is independent of data. It also takes on an integral value. That means, in particular, that you can compute it at any value. And it will always give the same. In fact, since the Hamiltonian contains all the other couplings that appear in the theory as well, it is actually independent of any coupling in the theory. H of x, some polynomial, let's say. And then the written index is independent of all this lambda. And also, if it takes on a non-zero value, then we know that supersymmetry is unbroken in the time state. opposite statement is not necessarily true. So it's not necessarily true that if this guy is equal to 0, that there are no supersymmetric ground states, because there could be a bosonic ground state and a fermionic ground state, and they could cancel if I equal to 0, it would still be suitably preserving ground states. But as I said, in our simple class of examples, the opposite statement is true, because we only have the bosonic ground state or the fermionic ground state. That's not a general feature. And so it is also useful to think a little bit more physically of why this thing is actually independent of beta or of the other couplings of the theory. So how to think about that? Well, let's look again at the spectrum of the theory. We could have some value of the couplings. There could be some energy eigenstate that is paired, because we're looking at the supersymmetric system. And now we can ask, well, what happens as we change the coupling? In general, the energy eigenvalues will depend. So this is the energy eigenvalue some state n will depend on the couplings in the theory. But so these guys, these states can move around. Eigenvalues can move around, but they always have to do that in pairs. Because by construction, this Hamiltonian is symmetric, so the spectrum, the non-zero energy spectrum is also always paired. So energies can change, but they have to do so in pairs. True, that same statement is true for ground states. So if we have a zero energy ground state, as we change the couplings in the theory, these ground states may fill to remain equal to zero states. But when they fail to do so, they have to do it in pairs. Because as soon as you leave the zero part of the spectrum, you have to appear in a pair, because that's this property of the supersymmetric. Because if these ground states live, they live in a pair, the difference will not be affected. So the set of ground states may change. We may lose equal to zero ground state as we change the couplings, but the difference in the dimensions of these limit spaces will change because they live in pairs. So that's the basic physical reason why the index is a protected quantity. It's independent of the couplings. And that's a very general statement, so that applies in this quantum mechanical system, but it applies more generally for supersymmetric quantum.
In this example, is it possible to construct deprivation so that there is no ground state of one type or other?
Yeah. Sorry. Maybe I wasn't entirely clear in the examples, but if I have a potential, well,
That's not what I asked. What I asked was the example you gave where things are lifting.
yes,
Is it possible that, so suppose there's more bosonic ground states or fermionic ground states. Is it possible to create a deprivation such that all the fermionic ground states lift so that the number of bosonic ground states is the index?
yes. So in fact, I think generically that is what will happen. So so if there, well, maybe that's not quite true. I guess it depends on the theory, but yes, that's certainly possible. Yeah. So we'll also see examples where we can explicitly construct the function, the Hamiltonian, such that there are only bosonic ground states, and then the index will actually give us the dimension, the total number of supersymmetric ground states, and they can't lift because there's no fermionic partner for them.
But presumably for the largest power go to zero, like the lambda highest power will
Yeah.
change, then something will change.
Then something will change. So
So that's
there's,
the only change, the highest power.
So, as long as the highest power, so there's a, deformations or the changes that you can consider in lambda are restricted exactly by this statement of cosines. So if we do that, if we change h of x too drastically, then the x can change as well.
You showed the example of x cubed. It's
Yeah.
different in the explanation there.
That's right.
But all the lower ones.
All the lower ones can change. Yeah, that's a great. So it's independent of the couplings up to this remark of Costas that you can't change the highest power.
And we're still only thinking of polynomials.
Yeah,
With explorable x there.
yeah, I mean, but yes, you could put there could be it could be exponentials. I guess I'm talking about these guys because, but the construction and all the things I've said hold for arbitrary, from an arbitrary real function h of x. Everything goes.
But it's an exponent, there's no higher power.
Um,
The highest power of x, so the index is fixed.
Yeah, I guess that probably that won't have this. So you're saying let's consider h of x to be e to the power x to sort of.
Or ln of x, any definite series.
So I guess those probably usually. Yeah. So then there is no highest power of x. I guess that in that case, yeah. So there is no supersymmetric constant in this case. So it feels that important. But the question is,
I was just asking if you only consider polynomials or it can't be any function.
there could be any function. Yeah. But I guess typically, well, these polynomials have nice asymptotic behavior. Asymptotic behavior. Okay, so now I'm going to show that that these properties of the index, the fact that it's protected, are quite powerful and allow us to compute the index exactly for a general field. So general Hamiltonian of the type we've considered so far. That's for the thermal partition function. If you want to compute the thermal partition function for a general potential, that's very hard because you have to solve for the spectrum of the field. And typically, you can only do that in perturbation. Right? But actually, the index can be computed exactly for arbitrary h of x. So let's see how that works. So computation. Okay. So the idea is to take the Hamiltonian, take the function h of x, that is the Hamiltonian, and we scale it by some number, lambda, times h of x, where we take lambda to be a large number. So by these general arguments, we know that the index should be independent. So we are allowed to do this without changing details. Then we're going to use that in our advantage. So in this case, we do this with scaling. The new Hamiltonian still have t squared plus lambda squared over 2 squared plus lambda over 2 threshold. Okay. This potential here becomes very steep for lambda very large. So, as such, the wave function of the states will only probe a very small region, delta x, around the critical points. The wave function will be very localized around the minimum of the potential, which are the critical points, right? So the critical points where h prime is equal to 0. Okay. Now, let's use that fact to expand the Hamiltonian around these critical points. Write the Hamiltonian. So, yeah, so let me first expand the function h itself. So h of x close to the critical point I, we're going to h of xi. Plus, then the linear term vanishes because it's a critical point, and then we get h. Second derivative evaluated at the critical point I times x minus xi squared plus higher order. Okay. So we plug that into the Hamiltonian, and in addition, we introduce these rescaled variables. So we're going to replace x minus xi, which is becoming very small. I'm taking out the smallness by square root of lambda, where lambda is very big. And then I have my still the I. Finally. And then I'm going to compute the Hamiltonian. But let me this. Yes, that the Hamiltonian is approximated. Some of these critical points, we get an overall factor of lambda, where and half the tilde square. So here the tilde is minus I dx dx tilde. That's it. I have a p squared and plug in the dx by dx tilde times square root of lambda. This p squared gives me power of lambda. And in addition, well, H prime is vanishing, but so this term gets a contribution from H to the half. H prime xi squared times x tilde minus x tilde squared. And then finally, this lambda is multiplied with plus we have this where the factor of lambda here just comes from the fact that we scale h of x. And sorry, I should also say that we have a lambda squared here, but the rescale variables take out this 1 over lambda square root, so that's why there's an overall lambda multiplying this stuff. And then there are various other terms from the Taylor expansion, but they contribute at lower orders in lambda. They are order 1 over lambda without half. Okay? For lambda large. So in the strict lambda to infinity limit, what we see is that see that h lambda to infinity, this becomes a sum of ordinary harmonic oscillators, pseudosymmetric harmonic oscillators for each critical point of the function h. Right? Because this is just some constant. It's just the value of the function at the critical point, the value of the secondary to the critical point. There's only this, there's only a quadratic part in the axis. Right? So what we've done is we've replaced our Hamiltonian essentially by the quadratic approximation to the Hamiltonian. But this approximation, so we can use this proxy Hamiltonian in the lambda to infinity limit to compute the index. But then, because the index is independent of lambda, that index will take the same value in our original field. So that's the trick we're using here to compute the index for general theory by simply reducing it to a set of harmonic oscillators, which we can solve for. So explicitly, what we get is that the explicit expression becomes as follows. So in the example, we had seen that depending on the sign of omega in the harmonic oscillator, right? So h double prime at the critical point plays the role of omega. Example. And this will become a bosonic ground state for h double prime larger than 0, and a fermionic ground state for h double prime less than 0. Let me write that down. So from the harmonic oscillator example, we have that's the ground state wave function is given by e to the minus a half h double prime x minus xi squared boson run H double prime at xi is larger than 0, it becomes the ground state near the critical point X. Is fermionic. So vector if H double prime xi is less than 0. Right? In the strict lambda to infinity, these are our ground states, the exact ground states close to the critical point phi. And okay, in the full theory, which is just that lambda equal to 1, is, as we said, these ground states may not all survive, they may live in pairs, but the index doesn't care. We can compute the index for this naive or lambda to infinity limit of the theory, compute the index, and then use the fact that we use the uniform with the general. So let me write down the expression that we get. Here. And then we'll be done for the day. You can just write down this. Write it as the trace over the 0 and minus this. Minus 1 to the and this equals plus 1 if omega, where h double prime is larger than 0, and minus 1 if h double prime is less than 0. We can write it as this sign. Sum over all critical values, we can write it as the sign of h double prime. Okay. And indeed, for our specific examples, so for this class of examples, this only takes on the value plus minus 1 or 0. Okay. That's just because the minima of h prime x, minima and maxima of h prime x squared, sorry, the minimum, they alternate. So the value of h double prime alternates. But okay, this is the formula, and that's yeah, that shows sort of how that this is an interesting observable, and that we can compute it exactly for a very non-trivial function. That is the main statement that you should take away from this. Okay, I think that's enough for today. Any questions?
Our aim is to prove that index is insensitive to the topic. But up to quadratic h double prime, right?
So,
the conversion up to quadratic corner.
yeah, that's, well, yeah, yes. That's because if you compute further corrections, you see that there's rest by powers of lambda. So in strict lambda to infinity limits, those terms do not contribute. That's the case. So sort of the quadratic approximation to in this case, to the index is actually exact. And we'll encounter that statement a couple of times. That also from the path integral expression, we'll encounter the statement that the one loop approximation to the computation of the path integral is exact. For related. Yeah.
It's just, yeah, it was argument to work because you need the second derivative of the variance, right?
That's
What
right.
happens with the second derivative?
Yeah, so that is indeed an assumption. Yeah, so I haven't been mentioning for some of those requirements. You're right about that. When the second derivative is equal to 0, let's see. We'd have to think what that means for the function. Maybe there's probably some saddle point or something like that, which would not correspond to a round state. But I'm not, can look at a example of such a function hx to see what's going on. So what has the second derivative function?
So of course, you have the second derivative vanishes. How does that affect? But for this argument, for the derivatives is already mentioned. Not possible. The zero thing.
Yeah, you sort of, I think that's when it's 0.
I think you can have, I think you have points with the first derivative vanishes. We have the numerator and you have to decide always.
Yes.
Okay, so not sure what.
Yeah, so I'm tempted to say that would then just not correspond to the ground state because it's unstable point in the potential. I guess it's also necessarily larger energy, higher than 0 energy. Yeah. Exactly. Probably helpful to look at an example. Maybe exhibit state feature on the grid line in front of it. But we can, yeah, whoever wants to stay, let's first finish up, and then we can look at the chart.
Any more questions? Yes, thanks, again.
So David was talking about how you make lambda arbitrarily large.
So we're still starting at 9:30.
Yes.
Then the minimum and maximum would be like very very stretched. So we expect the ground state to kind of peak around the minimum potential. Because just in general, we expect our ground states yeah, like a double well, that one transform. If you multiply that potential by a huge number, that minimum and maximum come sharper in the ground, it's like a tiny it's only non-managing.
Yeah, just,
So basically, we only need to consider.
That is actually a goal, and then
has there been this is.
How did I get second?
Yeah, so that's, I think he just used the formula we got earlier.
That is, it was like, then we were like, this is in all the terms, both the sides use the zero. When we introduced it, in one of them, it was always zero, and in the other one, it was even basis. It is like,
Like what?
like side error zero instead of zero and.
Right.
So initially what we had no.
Yeah, actually, I think.
Yeah, well, the harmonic oscillator case, it depended on sine of omega, right? Whereas in this case, omega
Which is fine, but what we had was we did not have any absolutes. Any other sine side or has in the exponential absolute. And then we also.
I should actually do the code. Let me stop the live.
Yeah, I think everything in terms of it was in terms.
Yeah, I understand this.
There is one